introduce the speaker. So we welcome Professor Satyavan Bhunia from Shah Institute of Nuclear Physics. So Professor Satyavan Bhunia did his PhD from IIT Kharagpur in 1999, and he was a scientist in DRDO from 1998 to 99. And he was a postdoctoral researcher in the University of Electrocommunications, Tokyo, Japan, from 1999 to 2002. And he was a postdoctoral fellow at NTT Basic Research Laboratories, Atsugi, Japan, from 2002 to 2003. And he was an assistant professor at IIT Bombay from 2003 to 2004. And he was an associate professor at Shah Institute of Nuclear Physics from 2004 to present.
And now he's professor. Now he's professor.
Now he's professor. Now he's professor in Shah Institute of Nuclear Physics. So Professor Satyavan Bhunia, he will talk on atomic scale ordering and effect in compound semiconductor materials. Okay. So with that, I leave the dais to Professor Satyavan Bhunia for his erudite lecture.
Okay, thank you, Professor Sanyal. And thank you, Professor Vor, for giving me this kind introduction. Also, my sincere thanks, especially to Professor Vor for giving me this opportunity to present this talk on this faculty development program. So, okay, without further elaboration, I'll go straight to my topic. So let me share my screen. Okay. Okay. Can everyone see my slides?
Yes.
Yes. Yes. Yes, it is visible.
Okay. So today in this talk, I will talk about natural superlatives ordering in compound semiconductors. So as you can see from the topic, it's it's actually very uncommon and very narrow topics. Mostly you won't come off of this topic mostly in the journals, but it's a very, very important topic. It's a microscopic phenomena that occurs in compound semiconductors. So it's being such a narrow and uncommon topic. So it is, and especially I was told that there are a few students also in this audience. So instead of directly going into the topic, I will first give some elaborate background and introduction about the compound semiconductors. What are those compound semiconductors? How you realize compound semiconductors? How do you get those compound semiconductors? And what are the basic use of these semiconductors? So even before going into compound semiconductors, also especially for the students, I will give some basic building blocks about semiconductors, right from the very basic beginning of semiconductors definitions, and how this band structure, not band structure, actually band gap evolves, and how these band gaps change when you go for different quantum material, that is low dimensional nanomaterials. We don't, in semiconductor, we don't call it nanomaterials. We call it quantum wells or quantum dots. So quantum structures, we call it. So I will just go through how those are realized and what do we mean by those terms. Okay. So this is the outline. So semiconductors, which are the backbone of all electronic devices and systems. Then briefly we will discuss physics of quantum structures. Not very elaborate physics, but at least basic one, which one is to refresh. Especially for the advanced researchers and teachers, this part may be a little bit boring because it's from the basic, but for the benefit of the students, I'd like to introduce these basic things. And then how do you realize these quantum structures using crystal growth? So we use a very, very specific type of crystal growth that is called epitaxial crystal growth. It's a very refined form of thin film growth technology. Then I will go to the topic of today's talk, that is natural superlatives ordering, why it occurs there. And of course, there are some examples of quantum devices. Okay, though of course, though it's listed here as a separate topic, but later on I decided that this part, different devices, will be intermixed in between the talks. So there won't be any separate item of this, but you will find those devices in between the talks. Okay, in between different slides. Okay, let me go to the next one. So semiconductors, as you know, these are the basic backbone of all electronics and modern information technology devices. For example, this computer through which I am giving my talk, or through which you are listening or hearing my talk, these are the computers which represents culminations of almost 200 years of research and technological developments. So first idea came in late 18th century. Okay, and then actually a workable computer was proposed by Professor Konrad Zuse, who was a engineer, German engineer, in 1941. But in those computers, if you see those early computers, and if you want to have those early computers having computation power same as today's device or laptop, then actually you need a huge computer, because in those earlier days, computer used to be built using valves, diodes, triodes. Probably nowadays students don't read those things. Diodes, triodes, these used to be vacuum tubes, vacuum valves. Nowadays I think they have taken off from the syllabus. But those are the bulky devices, but nevertheless very rugged devices. And if you see the early computers, which was of the same speed at today's computer, then it needs at least 30 ton in weight. Okay, 30 ton means each one normal truck is about 10 ton. So three of such trucks will carry one computer, and it will have 18,000 vacuum tubes, 500 miles of wiring, and all those things. But these things dramatically changed after a basic invention, major invention of the middle of the last century. This was in Bell Labs. Professor Graham Bell, who discovered this telephone. So he established a lab in Bell, which is called Bell Labs, and that labs is basically working all the time on semiconductors. Still, they are continuing to work on semiconductors. So one of those basic inventions in those days was by these three gentlemen, Bardeen, Bratton, and Shockley. And this Shockley, so this is an experiment. They discovered a transistor. It is not a vacuum transistor, but it's a metal to semiconductor contact transistor. So this is, you can see here, a germanium with a piece of germanium, and there's a metal contact, low temperature. Then they could find the current rectification. So diode actions they could find, and then later on they impoverished it to make it a transistor. That's why, and then these transistors were used to build the radios, because now you will see that people used to call transistor radios. Many a time, transistor radio means small radios, they used to call it transistor. That means those radios, they incorporate these solid state transistors. So for this discovery, these people got Nobel Prize. And then this particular invention actually changed the revolution or the face of information technology or computing business. So this is a remarkable technology. And then with this, people with further engineering, all those things have come, and we can get computer at your desktop or computer on your, just a second, something is disturbing me. Okay. So these things are built off. Okay, so this earlier invention, this was mainly based on germanium and metal. So now all these materials are, germanium has fallen off the radar now. Now most of the devices use silicon. So silicon constitutes about 98% of all devices, semiconductor devices. Silicon is still the workhorse of semiconductor industry. But silicon, though this is a beautiful semiconductor, it has certain drawbacks. It is not a very good semiconductor in terms of semiconductor parameters. The only good thing silicon has is one can grow a very nice native oxide on silicon, and that gives rise to MOS type of devices. But apart from silicon, if you see this part of the periodic table, this is silicon in group 4. If you look at the two groups besides silicon, say take a compound of gallium of group 3 and arsenic of group 5, then you can make a compound of gallium arsenide. Similarly, indium phosphide. These are compounds, but these are compound semiconductors. So these compound semiconductors are very, very important semiconductors, very nice semiconductors. And silicon means it has only one band gap because it is one material. But by choosing different materials, you can have different band gap semiconductors. Their mobility, that means electron speed inside the device, is much faster than silicon. Electron scattering or loss mechanism is much better in compound semiconductor than silicon. So we can have, depending on which compound, you can have gallium arsenide, this is a binary compound, or one can have gallium indium arsenide, these are ternary compounds. So these are all semiconductors, and these are compound semiconductors. So I'll tell you in details later on. Then apart from these 3, 5, one can also have zinc, selenium. So these are 2, 6 compound semiconductors. Cadmium, telluride. So this is cadmium telluride is a semiconductor which is used for digital X-ray imaging and all those things. So these are the compound semiconductors which has a very specific applications where silicon fail. Because as you will see in the later stage, silicon is material where it has the indirect band gap. So any electron that you excite to a higher excited state, that electron when it jumps to lower excited states, it comes through the phonon. So as a result, we don't get a desired photon output. Or even if you want to use it as a photodetector, the absorption process in silicon is weaker than this gallium arsenide or compound semiconductors. So in optoelectronics, where nowadays you have LED lights everywhere in your car, in your home, all these incandescent bulbs or the tube lights that have been replaced by LEDs. Then you have nowadays everywhere this fiber communication. So you have broadband with geo fiber and everything. So there you need to have sources as lasers, and that lasers are detected by detectors. All those are built up by these compound semiconductors, and even very high speed transistors, many things people use with these compound semiconductors. So basic difference about device technology is silicon. Silicon is something where you can use a monolithic technology. You just take a silicon wafer and then you can grow an oxide on this, and then you can define your source, gate and drain. Then one can have a transistor action on silicon. So you don't have to separately anything on the silicon. Similarly, one can make bipolar junction transistor using silicon. So you can do a sequential diffusion and make NPN layer in a single wafer of silicon. So then you can define your collector, emitter, base, and one can define a transistors. And these transistors can be defined next to each other, and then they can be a contact can be made from one transistor to another to make IC chips. So for this, you don't have to grow anything. Once you have a silicon wafer, you can go for it. But for the compound semiconductors, advantage is you can have different bandgap materials of different properties. For example, here you can have 3 different semiconductor materials: higher bandgap semiconductor materials, lower bandgap semiconductor materials, and again higher bandgap semiconductor materials. These smaller bandgap materials is in between 2 high bandgap semiconductor materials. And if you see the bandgap profile, if you take a silicon, bandgap is same everywhere. But if you see this one, here you will see one side is higher bandgap, lower bandgap, and higher bandgap. So this is something people call bandgap engineering. And then if you make it N-type, then you have electron source here. If you make it P-type, then you have hole source here. And then if you give a forward bias, electron can go to this well, holes can go to there. And then there is a confinement potential where you can force them to recombine, and then easily light can come out. So this principle is used for many quantum devices or heterostructure devices, optical devices, solar cells everywhere. So this is the basic building block. Okay. But thing is that how do you realize such a 3-compound material? So normally these are grown physically by crystal growth method, and that is called epitaxial crystal growth method. I'll go to this point separately. So so there are 3 different kinds of compound semiconductors, as I said. Gallium arsenide, indium phosphide, these are binary compound semiconductors, and these are also used as a substrate. So when you grow a thin film, you need to grow those thin films on something. That base material is called substrate, and these compound semiconductors are used as the substrate for those. And on top of that, one can grow binary compound or even ternary compounds, quaternary compound like this. The reason is, if you look at this diagram, this is a very useful diagram in compound semiconductor research. So this is in x-axis we have this lattice constants of different compounds, and on y-axis there are the band gaps corresponding to those compounds. For example, if you see the gallium arsenide has band gap of around say 5.65, and then it has a band gap of around 1.4, 1.5 at room temperature. Similarly, one can have indium arsenide. So indium arsenide have larger band gap, but it's a lower larger lattice constant, but it has a lower band gap. Now so gallium arsenide is sitting here, indium arsenide is sitting here. So, and if these are the binary compounds, you can make an alloy of gallium arsenide and indium arsenide. And for example, this is 100% gallium arsenide. And from this, if you keep removing few gallium atoms and start adding indium atoms to this alloy, and then go towards it, you can see the band gap start reducing. At the same time, band gap start reducing. At the same time, the lattice constant keeps on increasing. So these are very useful diagrams. So this is gallium arsenide, indium arsenide case, indium arsenide system. You can see gallium arsenide and aluminum arsenide system. Here gallium arsenide is here, and then if you remove all the galliums and replace all gallium with aluminum, you can see there is hardly any lattice constant change, but there is a large change in band gap. So this is very useful. So you can play around with different band gaps. So this is very useful material. So I'll come to this material later on of my talk. But when you grow these materials, say for example, you are choosing to grow indium gallium arsenide. If you see on the right side, this is 1.5 micron. So this band gap, this is the band gap of the material correspond to 1.5 micron. This is very important wavelength for fiber optic communications, because in this wavelength, when people do fiber optic communications, then there is scattering and dispersion loss is minimum. So to make a carrier or to make fiber optic communications using this, one need to make a source or lasers using a material which corresponds to this wavelength. That means it corresponds to this. So this is indium gallium arsenide. This is a very important material. One can grow indium gallium arsenide. So this indium gallium arsenide is grown as a form of very thin film. Now this thin film, when you grow, you have to, because this thin film cannot sustain on its own, it has to be grown on some material substrate. Now which substrate we will choose? You cannot choose gallium arsenide, you cannot choose indium arsenide, because if you choose this composition for this band gap, then you can see, so for this alloy composition, this lattice constant will not match, okay, with either with gallium arsenide or indium arsenide. So to make a lattice constant matching, one has to choose having the same lattice constant is, you can see, indium phosphide. So this indium gallium arsenide composition you can grow on indium phosphide substrate. Similarly, if you work on gallium phosphide and indium phosphide, this gallium indium phosphide, these red LEDs or red lasers, you can see this red part. This red LEDs is grown using gallium indium phosphide. Then this gallium indium phosphide is grown on gallium arsenide substrate. So this is very important band diagram. Now let us go to the basics. So how do you visualize a band? Okay. So if you take a single atom, say for example lithium atom here. So lithium atom is Z is equal to 3. One can have very sharp atomic orbit here, an atomic orbit there. So in between there is a forbidden gap. But this is atom, so you have a sharp line-like energy level. Now when you have two lithium atoms, then if you bring two lithium atoms very close to each other, then this wavelength and this wavelength, if they overlap, that means you are bringing two atoms very close and making a molecule, hypothetical molecule of lithium atoms. Then if these wave functions overlap, then this energy level and this energy level will split. Okay, so for two atoms, it's a single sharp energy level has been split to double. Now similarly, if you make an array, a one-dimensional crystal of lithium, then and if you bring n such kind of atoms, then each of these energy levels has to split into n numbers. Now typically in a solid state materials, for 1 centimeter cube, this n is around 5 10 to the power 22. Okay, that many atoms in one dimensions. So that means each of those energy level will be split into that many energy levels. So each difference between one level to another level is extremely small. You can see it's a very small value. So that means this band now has become a band, and this one has become a band. In between there is a band gap, and this band in between those energy levels are sort of quasi-continuous. So this is a physical visualization of how band structure or how band gap occurs and what are the band structures of each band. Okay, so for example, this will be called conduction band and these will be the valence bands, and then this conduction band of states is very close nearby, almost quasi-continuous. Now if you take a free electron, okay, if you want to build up this this picture from mathematical point of view, if you take a free electron, okay, I'll go quickly go through it. If you take a free electron and solve Schrodinger equations, you'll find this is traveling. This is just plane waves traveling in other directions. So and you can solve for your wave functions and apply momentum operators, and you can get the momentum. But there is being a free electron, there is no barrier involved, no energy barrier to stop electrons. So it's an infinite. It can have a range from anywhere to anywhere. So that means probability of finding the electrons is same everywhere in space. Okay, and this is the energy. But this will hardly occur. So what you will have is in a material or in a crystal is an electron in a box. Okay, so now again here you have something in a electrons, but it is confined in a some kind of potential where electrons are confined in this. So when you have this, solve this equation and put the boundary conditions, then you will see that when earlier k could take any continuous value, now k values will be split. Now this will be discrete k values, and these are the discrete k values. So n quantum number has come, and k value is inversely proportional to the physical dimension. So a is the length of this box, so it inversely proportional to a. And again energy levels has also become split. So a being a large value, okay, this large means how much large we will get to know on later slide. So these energy levels are extremely small, and these are the kx. For each x, y and z we can write these k values in 3 dimensions like this, where L is the physical. So instead of A, I am now writing L. L is the physical dimension of a crystal. So L is large. Now how do you arrive at an energy band now? So again, for this you have taken an atom having this kind of a potential profile, and then you can build your artificial crystal by bringing those atoms very close to each other, okay, and then solve for Schrodinger equation for each of these. Now for each of these 10 to the power 20 Schrodinger equations since cannot be solved, so what we do is we use this kind of block theorem, because we take advantage of the similarity of the problem, the equivalent of the problem. So we can write the potential at any place is repetitive potential with repeating length a plus b. Then if we use this, and we take we know the famous conic penny model. So instead of those the critical band structures, if we take a square wave band structure and then use the Bloch theorem, we get to know this. We can easily find that this band structure comes. Okay, and then in between these bands there is a forbidden gaps, and these are the band structure. These are the and there are infinite number of k values inside these band structures. Okay, now what are the energy bands? So what will be these energy bands? So if you have this one, the band, you take any band, how these k values or momentum values of those electrons will be, as you can see from here. As I said earlier, this k I have defined 2 pi n by L, right? So 2 pi n by L. Now here L, what I am changing L to n into A plus B. A plus B is the repeating distance after which the potential changes. That is, one can see this is the unit length of a crystal, and then there are n number of those lattice points. If you multiply n number of lattice points times each lattice constant, then it becomes the crystal dimension L, and K is become like this. So this n again, n being extremely large, very large value, 10 to the power 22. So one can have these k values, delta k values is extremely small. So if you take delta k n and n plus 1 difference, you will see 2 pi by n into n. So this k1 k to another k is extremely small. That means electrons are moving in the band almost freely, almost quasi-continuous. There is no, it doesn't see much of change in momentum when electrons move from one energy state to another energy state within a band. So if you want to draw the distribution in K or K space, if you want to draw for bulk 3D crystal, you will see that difference in K space is extremely small. So delta K x, y, z in any direction is 2 pi by n into this term. So n being extremely large, these are extremely small, and this is uniform throughout in x, y, and z directions. Now what happens? So these are the energy bands and energy how these. So we have seen these energy bands and how these energy density of states vary with energy. It is given like this. For 2D, 3D compound semiconductor or 3D semiconductors, it goes as e to the power half. So these energy levels as a function of energy will go as, sorry, not energy level, number of energy at any number of levels at any energy is proportional to e to the power half. Okay, so this goes like this. And how these are filled? So this is one band, this is one band, say for example conduction band, and this is valence band. So this is the density of states on this valence band as a function of energy, and then you have a probability of distribution. What is the probability of each of these states will be filled is given by this. So this is the function like this, and then if you multiply over this function, and this function, and then integrate from this energy to this energy, then you will find how those carriers which are there in the band, how those carriers will be filled. You'll see most of the carriers will come down to the bottom of the conduction band and top of the valence band. So there will be hardly any carriers on the higher up in the energy in the band, each bands. So that's why always people say that band gap means the energy difference between the bottom of the conduction band and top of the valence band edge. Now what happens if you change the crystal dimension in one dimension, because in 3 dimension you have all those 3 macroscopic dimensions. Now what we have done here is we have reduced one dimension, for example this z direction, to very, very narrow point. Narrow means, I mean to say, in few tens of angstroms. If you bring it one dimension to few tens of angstroms, then instead of this 3-dimensional material, what we have is essentially a 2-dimensional material or 2D crystal. So in this case again, one can solve this equation by method of separation of variables, and we can see this Ez has become, means energy of the crystal, energy of the carriers in the z direction have now become a function of the dimension on that side, on z side. So if you can now vary this value you can vary the energy levels of this carriers. So this is now the design parameter. You can have additional design parameters, and this is the basics of all your two-dimensional crystal, or in quantum terms we call it quantum wells. Okay, and if you see the distribution of now the K space, in the K space, which was earlier used to be a uniform distribution of K space in K points in K space. Now that has now changed. You can have sheets of K. So you have for one quantum number n is equal to 1, you have sheets of K space. That means electrons can move freely along this line, but they cannot make a jump to the other one, because then in that case it needs to have a substantial momentum change. That means it needs to have substantial energy absorption and then can go to the next energy level, and in the next energy level again it can have similar of K space, so it can move around. That means electrons now can move around freely in this direction, in these directions, but not in this direction. If you want to shift this energy in 3 dimensions on the Z direction, it has to absorb that energy. Similarly, if you go to one-dimensional case, again you will see this the K space distribution instead of sheets, it has become now rods. That means electrons can only be moved in this direction. So electron can move only on the direction of the nanowire, or in the direction of quantum wire. This is called quantum wire or nanowire. So in this direction electrons can move. So any device you want to make, only one-dimensional movement of electron is possible, and other directions, other 2 directions, electron movements are confined. And then finally you have zero-dimensional, that is called quantum dots. And in this case, again, instead of those one-dimensional distribution of K, you can have, now you have discrete distribution of K. That means electrons once are put in this, or electrons which are put in this ground state, it will continue to stay in that ground state unless it is excited by some means to go to the higher energy states. Okay, so here that means electrons cannot move. Electrons are totally confined in space, and these are called zero-dimensional, quasi zero-dimensional crystals, or quantum dots. And these are the comparative density of states for three different types of materials. I've already told for 3-dimensional materials it goes as e to the power half. For 2-dimensional materials, the the density of states are step-like. For where it is this kind of narrow distribution, and for dots these are very sharp. These are very sharp distribution, means these are similar to atoms. Right? In atoms you have a very sharp energy levels. So here also in quantum dots you have very sharp energy levels. That's why quantum dots are also called artificial atoms. Okay. Now the question is, okay, just I'll come for a minute. Okay, so so far so good. Now the thing is that we have described 3 different types of quantum structures. The question is, how do you realize these quantum structures in practical use? So these are, as I said, these quantum structures are typically grown on a substrate which hold these structures, and these are grown by a process called epitaxy. Sometimes quantum dots are also grown without epitaxy. These are grown with some chemical process. These are called colloidal quantum dots. These are also very useful dots, but we will not go into that kind of thing. We will discuss the crystal growth and how do you realize all those 3 kind of quantum structures. So what is epitaxial crystal growth? Now if you talk about the definition of epitaxy, so I would say it's a controlled growth of single crystalline thin films of a particular material. Okay, and each of these words in this line are important. Single crystalline, it has to be thin films on a given substrate. So in such a way that whatever you are growing on the substrate, that thin films would have a definitive crystallographic relationship with the underlying substrate. So anything you just cannot grow on any substrate or glass or amorphous, that will not be called epitaxy. So epitaxy will only be called when there is a, whatever you are growing and on which you are growing, so there should be a definitive crystallographic relationship. Okay, then this is called a epitaxy. So there are two kinds of epitaxy. So homoepitaxy means growing layer is the same as that of the substrate. That means substrate, if you are taking gallium arsenide and you are also growing gallium arsenide, then this is called homoepitaxy. Your substrate and your epilayer is same. But so also then there is a no problem of crystallographic relationship, because the lattice constant of the growing epilayer and the substrate is the same. So this point will come to there, that point will come to there, and there is no problem. But apart from this, there can be, because this is of a very limited interest, so this is not the reason why we study all those things. So there is another important thing, is the heteroepitaxy. Heteroepitaxy, we grow material of having different, heteroepitaxy means you are growing different materials than that of the substrate. Different materials means the different material can be of the same lattice constant of the substrate, but having larger band gap or smaller band gap, or it can be larger lattice constant material grown on a smaller lattice constant substrate, or vice versa. So these are called heteroepitaxy, but when you are growing, there should be a definitive crystallographic relationship. So these are lattice mismatch but coherent. When you grow, we'll see these points should come there, that point should come there, that point should come there, and then that will make a coherent growth. So these growth are done by normally three types of epitaxial crystal growth technique. One is called liquid phase epitaxy. This has become old now. Earlier it was very useful. Earlier lasers and LEDs people used to grow using liquid phase epitaxy. Now these are hardly used anywhere. Now there are two major epitaxial system techniques. One is called metal organic vapor phase epitaxy. This use metal organic compounds as the source, and another is called molecular beam epitaxy, or MBE. Okay, so let me go through quickly about these two techniques. So metal organic vapor phase epitaxy, it is also called, sometimes called metal organic chemical vapor depositions. Okay, so as you can see, the name suggests this epitaxy involved use of metal organic compound materials as source, and then this is used to grow materials on a substrate. So these are typical Emulsivity machines. One can see these are more than a height of a person, and these are epitaxial Emulsivity reactors, one can see. Okay, so if you want to let me just describe the process quickly. In a metal organic vapor phase epitaxy, you take a reactor, is a large size reactor, and then this reactor, inside this reactor we keep the substrate on which we want to grow the material. So that is called substrate, and that substrate is put on something which can be heated. So that is called susceptor. So the substrate is kept on susceptor, and the susceptor can be heated to a high temperature, typically 700 to 800 degrees centigrade, depending on which material you are growing. And then different organometallic molecules carrying those desired elements. For example, if you want to grow gallium arsenide, then we have a organometallic compound, trimethyl gallium, okay, trimethyl gallium, and then for arsenic we have arsine, ASH3 gas as source. So both of these are organometallic compounds. So this gallium, trimethyl gallium, is liquid. So this is kept in a bottle, and then through that bottle, ultra high pure hydrogen is bubbled through that bottle, and then some vapor of that organometal along with the carrier hydrogen is carried through this line and then brought to the reactor. Parallelly, from the other line, arsine is again brought through hydrogen, and again it is put in there and brought into the reactor. So you have brought in trimethyl gallium and arsine at high temperature, and then if at high temperature those molecules they break, and then those organometallic parts, organic parts are separated, and gallium and arsenic they react and they deposited on the substrate atom by atom. So this is called metal organic vapor phase epitaxy, or Movp or emulsivity. So typical organometallic sources for trimethyl, for gallium it's trimethyl gallium, for aluminum it's trimethyl aluminum, for indium it's trimethyl indium, and also if you want to dope it while growing gallium arsenide or indium gallium arsenide, you can add your dopant, which can also be an organometallic. So you can, so these selenium sulfide, these can act as N-type, and silicon or zinc, they can act as P-type. And this is a typical, you can see MOVP growth reactor. You can see it's a large scale, commercial scale size reactor. So these are the substrates one can see. And this is the susceptor on which the substrates, which gases are coming, and then they are broken up. The organometallics part, organic parts are separated, and then those gallium arsenide is deposited on this, and this is planetary, large scale planetary reactors. And this is the workhorse of all whatever LEDs, home LEDs, LED lights, decorative LEDs, your LED TV, large scale LED display, your lasers, sources, detectors, everything has grown through this, using this technology. Another very important technology is molecular beam epitaxy. So this is essentially ultra high vacuum system. Sorry. So in this ultra high vacuum system, around 10 to the power minus 10 torr in a chamber, we take a heated body that is called susceptor, on which we keep the substrate, for example gallium arsenide substrate on which we want to grow. So that substrate is kept, and then direct source of different atoms, for example gallium or indium, aluminum, arsenic, etc. These are kept in different bottles, just pure metallic bottles, and then they are heated up at a very high temperature, and this become ultra high vacuum. So these atoms become vaporized, and those vapor beams are allowed to fall on the substrate. So this is gallium beam, and then from the other side it's arsenic beam, then gallium arsenide is grown on the substrate. So like this one can use, and this is ultra high vacuum system. So unlike in Emulsivity system or Movp system, which is a gas based system, but this is ultra high vacuum system. So when you are growing crystal growth, doing epitaxy, you can really monitor what is happening during the growth. So this is a MB chamber. Then here there is a viewing port through which one can put a electron gun through this. The electron gun can fall on the substrate, okay, and then you can see the reflected electron beam, and you can see the reflected beam on this, and then when you grow, you see what is happening on the electron beam intensity. These details shall come later, you'll see. So this is a real-time monitoring on MB system can be achieved, but still, though there is some breakthrough in commercial use of this technique for commercial output of materials, but this is mostly still in the research level. In the labs, people use MB, and this is at large-scale commercial MB reactors. You can see the compare the reactor size and that of a person. So you can imagine how big is these machines. So general aspects about growth. So as I said, when you grow on some substrate. Okay, so for example, gallium arsenide substrate. Now this gallium arsenide, which gallium arsenide? Typically we take 100 oriented single crystalline gallium arsenide or single crystal indium phosphide or whatever in 100. So this is called vicinal substrate. Now when you take a substrate on the surface, doesn't matter how finely you clean the surface or how flat, optically flat you make it, but since you cannot break an atom, so there will be atomic scale roughness on the substrate. Okay, so these atomic scale roughness, they are called atomic steps on the substrate. So these steps, sometimes these steps are very important. So these are the characteristics of a substrate. You take a substrate, you make it ultra flat to the extent possible, and then you sometimes, most of the times, you make a specific miscut along on some asymmetric direction. So this is 100 direction. You take a miscut 2 to 4 degree miscut along 0, 1, 1. Then these atomic steps, they will be arranged on this. And then when this substrate is used into the growth, these atomic steps, they play important role in kinetics of the crystal growth. So these details will come later on. So you take this and then you clean this surface, because whatever crystal you take, it has got native oxide. Then you remove this native oxide using chemical treatment, and then you take this ultra clean surface and put this substrate either in your emulsivity reactor or MB reactor, and then you start growing. So typical growth cycle like this. So for example, you put the gallium arsenide into a substrate, then you start heating it, and you start heating, then you protect your surface by group 5 materials, arsenic source, and then you bring it to high temperature, growth temperature, you grow it, and then you cool down. Now this is a nutshell in epitaxial process. Now this epitaxy process, though I said I described emulsivity process or MB process in a very casual manner, actually this is a very complex process. And though earlier it used to be a black box, people used to treat it like trial and error technique, but nevertheless nowadays many things has been understood. So there are 3 basic aspects of any crystal growth. First is mass transport. So when you are carrying your source materials from source bottles to the reactor or to the substrate surface, so there's a mass transport. What is happening on the mass transport, whether the reaction is occurring during the gas phase or not. Then thermodynamics, because when you are growing crystals, you have to grow crystals in unsaturated mode, because you cannot grow crystals in equilibrium conditions. In equilibrium conditions, you cannot deposit crystals. So certain level of non-equilibrium level has to be kept. So that is modeled by thermodynamics. And then finally, what is actually happening on the surface, the kinetics. So these 2 processes, so these are very important, but for the time's sake, I will not go into these details. But this is being little important, and so I'll just go through this, what is happening on the kinetics during the growth. So microscopic surface process during epitaxy. So so as I said, when you take a substrate, for example, you are taking a 001 substrate. For example, here is the 001 substrate, and then this is the atomic structure of the 001. So you can see this is the top surface. Here are the atoms, and here are the atoms. But since you cannot break these atoms, so this atomic scale roughness will always remain. So this is called atomic steps. And if you make this crystal little bit, if you make this cut intentionally towards 110, then this is a regular array of atomic steps one can have, and these are very important. So if you draw this in this kind of schematic way, so here you can see, say this is one atomic state, this is another atomic state. So this is a part of the substrate surface, and here you can see those lattice points. So here the crystal growth will take place. So for example, here you are allowing your crystal growth to take place. That means in emulsivity, your gallium and arsenic atoms are coming, and they are coming to the surface on this. And then after this, when they come on the surface at high temperature, each of these lattice points are vibrating. And these add atoms, when it comes, it just doesn't get stick anywhere. On the surface, it undergoes a surface diffusions in random directions anywhere before it gets stuck to somewhere. So what happens is, if you model this surface like this is a sort of potential landscape if you can draw. So the add atoms comes here, you can see series of potentials here. So actually what happens is, see all these add atoms is coming at high temperature. This is having thermal agitations. These crystal lattice, these are also having thermal agitations. And then when it comes, when these vibrations and these vibrations are in phase, they get stuck. Once they get stuck, the add atom gets stuck on certain lattice points. Then its effective mass increases and its vibration dampens, and then again with that dampened thing, it can act as sink of further atoms. So once one nucleation has been occurred, then that nucleus can grow bigger in size. So this is the basic microscopic process that occurs during the epitaxy. So these atoms, when it comes, it can hop around due to high temperature using this formula, and then when it matches in phase with the atoms, then it becomes stick to it, then its potential drops, and then further atoms can be attached here, and then crystal growth takes place from this point. So depending on temperature and type of substrates, there can be three different types of growth. So first is, I call step flow of growth. So here, this is one atomic step, this is another atomic step. One atom is coming, that is, for example, gallium and arsenic, they are coming, and then if the temperature is large and this diffusion length on the surface is bigger than this terrace width, then most of the atoms, before getting stuck to these lattice points, they will migrate and stick to this surface. Similarly, those atoms which are coming on this surface, they will go and stick to the surface. And this step will flow. The step will grow like this. This step will grow like this. And this is the way the perfectly fine two-dimensional crystal growth takes place. So it's a very smooth and very perfect crystal growth can take place. This is called step flow mode of growth. So you can see this is an STM image in MBE growth. You can see these are the atomic steps. Okay, then they have grown. So what they have done is they have grown. They have calculated the growth time in such a way that before one complete terrace is grown, that is one complete monolayer is grown, they have stopped the growth at different points. So for example, this is the starting surface, and they have stopped the growth after quarter of a monolayer deposition. And you can see the atoms have been attached to the surface. So these steps are advancing, and this is after half monolayer. You can see the steps have advanced further, and this is after 0.4 monolayer. So these steps, almost one monolayer has been covered. So this is a very nice crystal growth method. This is one sort of crystal growth, this kinetics. Another one is two-dimensional layer by layer growth, or this is called van der Merwe mode of growth. This is actually very important crystal growth. So here what happens, this occurs at little bit intermediate temperature. So in intermediate temperature, the diffusion length is less than or equivalent to the terrace width. Now, as I say, I have already said this terrace width can be controlled by level of miscut on the crystal. So this terrace width can be varied. So if your terrace width is large, then crystal, when these atoms will come, they will stick somewhere, and these individual nucleus will start to grow. It's like water drops falling on some leaves, okay, and then more and more water drops comes. So these water droplets will grow bigger and bigger. So this nucleus will grow bigger and bigger. This nucleus will grow bigger and bigger in 2 dimensional, not in 3 dimensional, because our temperature is high. So surface diffusion is still large. So they will grow bigger. This will grow bigger, and then finally this one will collide, and one complete monolayer will be grown. Okay. So this is called two-dimensional layer by layer mode of growth. And then when your growth temperature is very low, then what you have is a van der Weber growth of mode. That means in this case, wherever your atoms is coming, they don't have sufficient thermal energy, kinetic energy to move around. So they will get stuck on top of each other, and this is three-dimensional defective crystal growth, and this is undesirable. Okay, so these three types of crystal growth can be beautifully monitored in MBE, because as I said, MBE is ultra clean kind of growth, ultra high vacuum growth. So what people do here is, so this is the substrate on which you are growing. You have gallium atoms, you have arsenic atoms, and then you are monitoring this by shooting an electron beam on the surface, and the reflected electron beam is detected on a fluorescent material. So initially you will see a very sharp spot. Okay, this with time, when you are growing, with time you monitor the intensity of this spot. So what happens is initially you have a very smooth shining surface. So electron beam is coming and it will go. So it will have a very almost similar intensity, a large intensity. Now you have grown about quarter of a monolayer. So you have grown about quarter of a monolayer. That means your surface roughness has now increased compared to this. If surface roughness increased, then your electron beam will get scattered. So on the screen, you will see less intense electron beam. That means intensity, which electron intensity on the on the fluorescent screen, which was strong, it will go down slowly. And then when half a monolayer is grown, that means half of that surface is covered, this your roughness will be largest, so intensity will become smallest. Then after half monolayer is grown, so instead of further roughening, it starts to become smoothening, So it is becoming wetting. It is completely making one complete monolayer. So roughness will, so that means intensity will recover again. And then finally, when one complete monolayer is grown, you can have intensity totally recover. So that means by counting this, how many numbers of oscillations you have, you can really know how many monolayers you have grown. Not only how many monolayers, you can even think of growing fraction of a monolayer, some monolayer quantum dots. These are very, very important things recently people are doing. Now, so apart from these three crystal growth method, there is another one which is very important. This is called Castanov crystal growth mode. So in all those earlier crystal growths, I have taken all the growing material and the substrate materials having almost similar lattice constant. So this may have different band gap, but lattice constant assumes to be similar. What happens when you take a epitaxial material having larger band gap, larger lattice constant than the substrate material? So when you grow this, what will happen? First monolayer, this one will try to come here, this one will try to come here, and this one will try to accommodate here. So as a result, if there is this much of lattice mismatch, as a result, there will be deformation in this cubic lattice constant. So when it wants to conform to this lattice site of the substrate, then it will increase in dimension on the vertical direction. So as a result, this will become strain. So there will be a lot of strain involved. And then when you grow few monolayer larger, then increased strain will push the material this from this side and this side, then it will make a helix like this. Then those helix becomes quantum dots. So once you grow like this, so that means there's a rearrangement of materials, and these materials will grow at dots. And then once you grow, so for example, this is gallium arsenide, this is indium arsenide. So large lattice constant indium arsenide, you are growing on gallium arsenide. So you can grow indium arsenide quantum dots. And then again, you cover this, after you grow the quantum dots, you cover this by again gallium arsenide. And then on this top of this, you can grow another layer of quantum dots. So this is the way you can grow quantum dots. So these are the different quantum dots you can see. Also, there is very interesting epitaxy called strain layer epitaxy. Here, if you take a large lattice constant material, then as I said, you can have compressive strain on this. If you take smaller lattice constant material, then you have a tensile lattice constant like this. So these materials are having different properties than its bulk counterpart. So their mobility is better, their electron scattering is less. So these are also used in various devices. But there is a limit to which you can grow. So if you grow this lattice mismatch or strained epitaxy for a large thickness, then after certain thickness, this material starts to relax and then it becomes useless. But nevertheless, there is a certain thickness available, which is called critical thickness. One can calculate. So if you keep your thickness less than the critical thickness, this material is very useful, and this is used in different devices. Okay, so let me skip this. Okay, now how do we make quantum wells? Let us see. So you take a large bandgap semiconductor and you take a small bandgap semiconductor. And then when you grow on top of each other, we have what is we call is a heterostructure. So you have a heterostructure. So this is a large bandgap semiconductor and this is small bandgap semiconductor. And then you take another large bandgap semiconductor, then this becomes a double heterostructure. Okay. So here in this, if you see this conduction band profile and valence band profile, there is a discontinuity in band structure, and this discontinuity gives rise to, so this conduction band discontinuity, this valence band discontinuity. And this band discontinuity gives us nice thing here. This gives rise to a potential well. So this is another potential well. This is a potential well for electrons. This is a potential well for holes. Now, if you make this thickness, if you make this thickness sufficiently small, because now you are growing by epitaxy, as you can say, you have already. I have already told that how precisely one can grow in epitaxial methods. One can really control to the thickness of monolayer, of half a monolayer. So one monolayer is typically of the order of 2.5 angstroms or so. That means you can control to that extent. So easily one can grow a thickness less than 100 angstroms. So if the thickness is less than 100 angstroms, then this well is called quantum well. Okay. So this is a typical quantum well, gallium arsenide, low band gap material, large band gap material, aluminum gallium arsenide, very thin. This is a cross-sectional ACM pictures of quantum well. And then when you have carriers confined in quantum wells, these carriers will have different quantum energy levels. As I said, discussed in earlier slides, that when you bring down one dimension to the to quantum regime, then these energy levels will split, and so at different energy levels, and this distance become now the dimension. This is a playing ground of my physical dimension. So this distance I can control, and if I can control this distance, I can change this quantum energy levels. So one can make device using this. If you can change, so we have a band gap, we have a material whose band gap is fixed. Okay, for example, gallium arsenide, its band gap is fixed. But when you grow it very sufficiently narrow, in addition to this band gap, you have another design parameters, which is a physical design parameter, the physical dimension, by which you can tune these energy levels. So by this, you can really tune the color or tune the wavelength of this device. And so first semiconductor device I will speak here. This is about semiconductor lasers. So laser, as you see, you have excited state and you have a ground state. And if you can achieve some population inversions by high pumping in a solid state materials, you can have lasing. In semiconductor, what will happen? What we do is we take you have a conduction band here, we have a valence band here. Typically, this is in the form of heterostructure. So this is in the form of heterostructure like this. So you have a conduction band, and then so here one can, on the one side, one can throw electrons. So this is the conduction band. In the forward bias, one can have accumulation of electrons in the conduction band and accumulation of holes in the valence bands, and they are being confined by potential well. So they are forced to recombine, and this becomes a source of laser or LED. So whatever lasers or LEDs you are getting is all based on this simple mechanism. So this is our light emitting diode. So okay, let us skip this. So this is a typical what it called. This is a typical double heterostructure laser. It comes out through this. So you have grown. What I mean to say, these lasers can be, or it has to be grown by epitaxial materials. Different layers of these laser structures are grown on top of each other, and you can. This is P type and this is N type. On forward bias, hole injection from the lower side, electron injection. They are allowed to accumulate here, and then they recombine, and then emission takes place from the side edge. Now, once this emission takes place on the side edge, now this, as I said, this has to be those photons have to be confined into the in the active region, because if there's a leakage of the photons, then you cannot have a laser oscillations sustainable. So, but what is happening here is, because as I said, double heterostructure means this is from here your lasing action is taking place, but on the other side you have a large band gap material and you have a large band gap materials. This large band gap materials means is a lower refractive index. So my photon is being generated here. This photon is confined by two small refractive index. So as a result, what will happen is these photons will confined in this active region, So by this we are allowing, forcing the electrons and hole to recombine to generate the photons, and those photons are remaining confined by this refractive potential, refractive index discontinuity, and this remains here. So as a result, your lasers will come from this. Now these lasers being operated through electric circuits. So on the electric circuits, you can put your signal or the data which you want to transfer, and then that can be modulated. So this is the practical laser structures, and all those layers are grown by different epitaxial methods, mostly by emulsivity method I described earlier. Simple laser structure, you can see how many layers people have grown. So these lasers are basically side emitting lasers, typically useful for fiber optic communications. So one can bring your fiber optics to this and couple the laser with the fibers, and then that lasers can go into the fiber and it can be transmitted. But apart from this, nowadays there are various surface emitting lasers. So these are the lasers which can emit from the surface, and this is grown by this called distributed okay, so this is a surface emitting lasers, and these lasers are people use nowadays for Apple device, where you need to unlock your mobile device using face unlocking. So in that device you have different surface emitting lasers. That laser shoots at your different parts portion of your face. Then the reflected beam is collected, and then face recognition is taking place. So this is a single quantum well. Then you can grow, if you take a practical quantum well, in ideal quantum well, as I said, electron wave function I have terminated there, but this occurs when your potential is infinite. But infinite potential is really one cannot achieve. So in a practical quantum well, where finite barrier, some part of your electron wave functions will go into the barrier layers. And when you have two successive barrier layers very close to each other, then these are called coupled quantum wells. So there can be multi-layers and there are coupled quantum wells. So when you have two quantum wells very close to each other, then this sharp quantum well and well level, this sharp quantum well level, this will again split in a coupled quantum well. And so this is one quantum well, and these are many coupled quantum wells. So if you are having these many coupled quantum, so the single quantum well quantum levels, you can see these discrete quantum levels. And when you have large number of interacting coupled quantum wells, then those sharp levels, they will interact, and this will make a mini bands. So these are called superlattice structures. Okay, there's a difference between superlattice and multi-quantum wells. Multi-quantum wells means different quantum wells without talking to each other, and superlattice means quantum wells which are overlapping with each other. So these are called artificial superlattice. So where each quantum wells these wave functions are overlapping to the next quantum wells. So instead of single discrete energy level, now we have an array of band of energy levels. Again, here have a band of energy levels. Now this is not this. See, this is the basic band gap, material band gap, and this is quantum energy levels. They are again getting split. So these are called intra-band splitting. So these levels, these energy levels are these energy band gap are very small, and if you convert these energy levels to micron or wavelength, this becomes 100 micron to 40 micron. That is the heat waves or IR, which our body emits, or different radar. So these are the devices people use in very strategic purpose, either in missiles or in infrared devices like this. Okay, let me skip through. I think I'm deviating too much from the basic part. Okay, so another important thing is the reason that why we are trying to work at Emulsivity is very specific applications on high efficiency solar cells. So if you take a silicon solar cell means, if you take a what is the basic thing of solar cell is, you take a band gap material having certain band gap, and if photon of having energy larger than the band gap, then this will excite one electron, leaving one hole, and then if you can collect these electrons and holes, then you can get charge or you can get electric current, and that is the way you can get so from photon you can get electric current. So this is silicon. So this is a basic of a solar cells. And if now in silicon is the two kind of semiconductor, as I said, this direct bandgap semiconductor and indirect bandgap semiconductor. The silicon, most of the solar cells that you see, these commercial band structure silicon solar cells are made of silicon, but silicon is indirect bandgap. So when they are absorbed through a phonon. So there's a heating process is involved. And if you take a direct bandgap semiconductors where the edge of the conduction band and top of the valence band in the same K points, so these are easily there, these photons is absorbed or emitted. So these are the direct bandgap compound semiconductors. Now for a silicon, for example, silicon bandgap, so if you take this picture, so silicon bandgap is around 1.1 electron volt. So any photon having energy more than 1.1 electron volt, that means if you take the solar spectra, only this much part of the spectra will give you electric current. Lower energy spectra will simply pass through silicon and they will not contribute to the current. So as a result, you cannot increase the efficiency of silicon too much. Again, photons which are having energy very close to the band gap, they are efficiently absorbed. But photons which are having higher energy, this extra energy, again it is lost. Again it is lost by thermal process. So in a sense, silicon doesn't give rise to very high efficiency solar cell. But apart from these solar cells, there are very specific types of solar cells where cost is not important, but efficiency or current output capacity is more important, are very useful in a very specific purpose. For example, this is International Space Station, where you can see large part solar cells. These are actually different types of solar cells. These are not silicon solar cells. These are called multi-junction solar cells having efficiencies more than 50%. What is the philosophy here? Here, so instead of one bandgap material, silicon, here we take 3 different materials and we want to grow 3 different materials on top of each other. So on the top, we have large bandgap materials which can absorb higher energy part of the solar emission. Lower energy portion will pass through this blue portion, and then we have after this we have a mid bandgap materials. So this part of this spectrum will be absorbed there, and then whatever remaining again will pass through, and then lower case we have a small bandgap material which will absorb the lower part. So here we can take care of energy as well as we can take care of all photons of the solar spectrum. So this is the purpose to which we are working, and I'll come to that later. Then I think don't have much time, so I'll skip through this part. So this is another way of growing nanowire. So let me pass through this. So these are quantum dots I have already discussed. Okay. So now let me come to the main topic. So natural ordering in semiconductors, for which so far was basics about crystal growth, semiconductor materials, etc. Now what is natural ordering? So this is, before going into this, materials we grow using our Emulsivity system in SINP. This is the system, and this is the different capabilities we have at our institute. Then this is the details of the Emulsivity system. We try to work on conventional semiconductor, compound semiconductor, that is indium, gallium, aluminum, and arsenic phosphides. And we use zinc for P-type and silicon as N-type doping. Okay. So this is our vertical reactor. So these are 3 wafers one can put, 2-inch wafers. This is the before growth, and this is after growth of some layers. So these superlatives or natural ordering, this came as a okay, so to see the background, why people think of natural superlatives. When people were working on a very specific material system, gallium arsenide, gallium indium phosphide material system, which is used for red LEDs, as well as heterostructure bipolar transistors, and this gallium indium phosphide is lattice matched to gallium arsenide for these particular compositions, almost same type of gallium and indium compositions. So when people were growing these lattice matched material on gallium arsenide, then depending on growth temperatures, okay, when you do X-ray diffractions on this, you get the same lattice compositions, but people were used to get different band gap, or photoluminescence. If you do the photoluminescence peaks were found to be at different energy levels, even for the same compositions. So earlier days, it used to be called as anomaly, because it was the physical origin of such difference for the same compositions, alloy compositions, were getting different band gaps. So this was not understood properly. So initially it was called an anomaly, because anything in physics or you don't understand, and which is close to your main explanations, is called anomaly. So as long as you don't understand, we call it anomaly. But later on, people looked at it very carefully as to what's happening in the macros or in the microscopic scale. So if you see the crystal structure of, say, any compound semiconductor, for example, gallium indium phosphide. So this is 001 direction. That means this is 001 direction. This is 1 directions, and this is 1 bar 1 directions. So this is my 001 surface plane. This is my 001 surface plane. So this is gallium atom. This is indium atom, and in between we have phosphorus atom. So corresponding to phosphorus atom, we have gallium bond, we have indium bond. Okay. So if you take 001 plane, in 001 plane, so you have, if you look from the top, it's a random mixing of gallium and indium atoms for each phosphorus atoms. Okay, so this is equal mixing because there are equal stoichiometry 0.5 0.5, so there will be equal mixing of gallium and indium atoms on the surface. But if you take this one directions, this direction, these planes, these are called polar planes, then you can see these phosphorus atoms are here. Then to this phosphorus atom, one side is you have gallium atoms and one side you have indium atoms. But the reason is, the question is, in this plane, why, or there is no reason to assume that this particular plane will only contain gallium. Ideally, this plane will contain equal mixing of gallium and indium. Similarly, this plane will contain equal number of gallium and indium. But what you can see here is this is segregation. So one plane is composed completely of gallium, which are bonded to phosphorus on one side, and then other plane is completely indium. So this is called natural segregation or natural superlative. This occurs naturally depending on the growth conditions or growth temperature, gas growth rate, etc. So in random ordering or in normal case, what will happen? Each of these planes will contain equal number of gallium and indium. So that is called completely random phase, and that is a normal phase, and this will give a higher bandgap material. But if you in a narrow growth window, if you don't take care of that growth window, what will happen? Your atoms will segregate. They will try to segregate on thermodynamic conditions, favorable thermodynamic conditions. Then this will give indium phosphide, gallium phosphide, indium phosphide. So this means phosphorus, gallium. So gallium phosphide, then indium phosphide. So this is a superlatives of gallium phosphide, indium phosphide on one monolayer scale. So this is, everything is happening in one monolayer scale. So this is called copper platinum type of ordering, and this is the reason why it gives rise to anomaly in bandgap. So if this plane is completely composed of random mixing of gallium and indium, then it will have higher bandgap or higher energy photoemission peak, and if it is segregated, then its bandgap energy will reduce. And if you see it, so first it was the microscopy people, the Suzuki. I met him in Japan. So it is first the microscopy people who could take out this explanation. So they did very high resolution electron microscopy. In normal electron microscopy, it won't appear. And also you need to have a very special sample. So they could see the segregation of these different gallium and indium atoms, and these are the bilayers. And if you do transmission electron diffraction patterns, so if you have a completely disordered material, that means complete mixing of gallium and indium, then you can have just corresponding to gallium indium phosphide alloyed compositions, electron diffraction spots. If there is a additional rearrangement like this, then you have additional super spots. So from these super spots, these are the ordered structures. So this gives rise to ordered structures. So this is microscopic ordering that takes place in compound semiconductor. And this is the topic I wanted to discuss. So this is the reason. And if this, so later on, this phenomena was discovered in many important compound semiconductors, for example, aluminum, indium arsenide. These are all used in, some is used in green LEDs, some is used in yellow LEDs, red LEDs. Again, here in gallium indium phosphide, it's a monolayer. Here you can see the ordering in 2 to 3 monolayer scales. Now, what is the manifestations? So if there is an ordering, its band gap reduced to change. So that means, depending if it is a complete, so this band gap reduction can be given like this. Eg band gap is Eg when S is equal to this order parameter minus delta Eg S square. So if S is 1, that means this is complete order, then this delta Eg is 0.38. That means for complete ordering, your band gap will reduce by a substantial amount, 0.38 electron volt. 380 millielectron volt band gap will reduce. And if it is completely disordered, then you have a large band gap. So that means if you are making red LEDs using ordered material and disordered materials, its colors will be different. Without knowing the microscopic thing, people won't know why these colors are changing. And also in many band structures, as I said, these band alignments, any heterostructures, band alignments, though I have given a very simplified band discontinuity diagram in heterostructures, but when you design any heterostructure device, so these detailed bands alignments are calculations are required. So for example, this is gallium indium phosphide, gallium arsenide band alignment, and here you can see band discontinuity. But if this band gap changes due to ordering, then entire band alignment changes, and your carrier propagations, carrier scattering, everything will change. In our case, what we did is, as I said, we were trying to grow this kind of multi-layer semiconductor structures for solar cell, multi-layer solar cell structure. So to start with, we wanted to grow some aluminum gallium arsenide, quantum well materials. So before that, one need to know for every machines, every emulsivity machine or emulsivity machine, you need to have a precise growth rate. So what we do, we grow a thick gallium arsenide or aluminum gallium arsenide for a large amount of time, say for example about an hour, and then we can calculate the growth rate per second. Okay, so in 1 hour we can grow this much, so we can know what is the growth rate. So this is my gallium arsenide. This is grown gallium arsenide. This is a cross-sectional SEM, and this is grown not a very good picture. This is a aluminum gallium arsenide. Again, to calculate the growth rate, we did this thick aluminum gallium arsenide, and we determine its growth rate. So this growth rate is this much. Then we were planning to grow multi-quantum well structures of gallium arsenide, aluminum gallium arsenide. So we wanted to grow 3 quantum well structures having quantum well width of 35 angstrom, 55 angstrom, and 75 angstrom. In between, large band gap barrier material of aluminum gallium arsenide. Personnel, is it okay with time?
10 more minutes.
Take
10 more minutes.
Okay. So so this one we were trying to grow, and then this is a cross-sectional TM structures of 3 quantum wells. And then fine, we got 3 quantum well PL peaks at low temperature, perfectly fine. So this project was given to a student to calculate this quantum well width versus interface roughness. So for this, interface roughness can be determined by X-ray reflectivity. So when we did the X-ray reflectivity of this in these materials, so we got very sharp peaks like this on this thing. So these sharp peaks were really not understood. Normally, this aluminum gallium arsenide system is very common materials and this has been used since 1960s. So this is used normally, but this phenomena has never occurred. We got very sharp X-ray peaks. Then we tried to do a rocking curve analysis of those structures. There also, apart from the main peak, we found very sharp peaks. Then it was bit awkward to know why these peaks were coming. So then we went to see very closely the cross-sectional TEM, and you can see the dark fringes, these barrier layers. So that was something which was not expected. So then what we did is we took the aluminum gallium arsenide substrate and then did its rocking curve. So here 004 rocking, 004 means it will give my because 004 is 002 is forbidden for gallium arsenide. So we go to 004, and in addition to the main peak corresponding to substrate and epi layer, we get very sharp peaks. So then we wanted to see what is happening in 002 in the forbidden. So in the forbidden here also, when the material related peak is gone, but your extra peaks have become very sharp. So these are something which are, that means there is some kind of layering was taking place. Then okay, if you compare like this, then in reflectivity also very sharp peaks were coming. Then we went back to our electron microscopists and see closely what's happening. Here we can see very again dark fringes on this. So this is a sort of, this was unintentional. This is a sort of natural superlatives ordering taking place. And then if you see very closely, in addition to the main, so this is electron diffractions. And if you see this, if you do the elemental mapping of these layers, so this is aluminum gallium arsenide. So we did aluminum gallium and arsenide mapping. Here also one can see these dark fringes. Okay, so we did the transmission electron diffractions in the multi-quantum well, and if you see closely, very closely, the main spots, then you can see close to the main spots, you can see those extra superlative spots. And then if you see the photoluminescence of the alloyed, random, and disordered and ordered materials, you can see the change in difference. So this is disordered materials, and this occurs when materials is ordered. So this is the first report of natural ordering of this scale in aluminum gallium arsenide. So then we wanted to see its temperature stability, how stable are these. So we wanted to we heated the temperature, annealed the aluminum gallium arsenide at different temperatures, high temperatures, and we found they are pretty stable up to 800 degrees centigrade. They were stable, and they becomes disordered at when you grow at 900 degrees centigrade. So here also like this. In reflectivity also similar thing happened. Then such nanoscale modulation in composition is very difficult to determine by SIMS or any other profile. So to get the monolayer or monolayer repeat distances, we have to depend heavily on simulations of X-ray data. So standard X-ray package will not work. So we did our coding using this kinematical theory of X-ray diffractions, and then we simulated these structures, and then from this we determined that the superlatives period is about 5.1 monolayer, and these were the different parameters. So these we could simulate from X-ray diffractions. So these are something that these large scale, though people have discovered superlatives or natural superlatives ordering in monolayer scale, in large scale in these materials, it was never reported. So we have reported this, and we could determine this one. And then from X-ray reflectivity analysis, we could determine the compositions of each of those layers of bilayer. So from this, we could determine that it is aluminum, which was supposed to be 0.2. Now you can see one monolayer is aluminum having 0.17, gallium 0.83. The next layer is aluminum. So this is a repeat bilayer of this one. This keeps on repeating, and this gives natural superlatives. Okay. Now we wanted to we heated the material at high temperature, and we simulated with we wanted to determine the interdiffusion coefficients using simulation using X-ray diffractions in conjunction with fixed law of diffusions, and then from this we could determine by simulations we could determine the diffusion coefficients at different temperatures. And then then finally we wanted to see whether these materials can be put into use in some kind of devices and planar devices. So these devices we had made. So we made a metal semiconductor metal photodetector. It is a planar device. So we made two devices, one using as-grown materials, one using the layered materials, and one using one using as-grown materials, one using material annealed at some temperature, and then another using disordered materials annealed at very high temperature.
5 minutes.
Yes. So you can see this. If you see the dark currents is much for as-grown materials is much lower than the ordered materials, and then okay, I'll go responsivity, detectivity, and sensitivity are all high for the as-grown materials as well as high temperature materials compared to disordered materials. And then we tried and we did time dependence. So we wanted to see how time response of these devices. So we tried to detect this chopped light, and we can see that for the device having ordered materials, this frequency is much higher compared to the materials device made using disordered materials. Okay, and with this I come to the summary of my talk. So I discussed basics of compound semiconductors and physics of quantum structures and different dimensions, epitaxial growth of compound semiconductors, and then natural superlatives ordering in compound semiconductors. So with this, I come to the end of my talk. Thank you for your patience.
Okay, so we thank Professor Satyavan Bhunia for a very interesting talk, and you can stop sharing. So the session is now open for questions. If the participants have any questions, they can write in the question and answer or in the chat box.
Participants are requested to kindly post their questions in the question answer section or in the chat box. If you have any questions and you want to know any information related to the topic, please post it in the chat box or in the question answer session. We are open now for the question answers. So please post your questions if you have any question.
Professor Bhaur, you have any questions?
No, Professor Bhunia already mentioned so many things. So I have nothing to say anything.
Actually, this topic was being very narrow, so I thought some basics should be discussed.
Okay, you have done it very well because you have given details about all from the basics to experiment. how it has been developed, and ultimately from developing the theory, how you have fabricated it in the laboratory, and after fabrication, how it is tally with the actually theory, and that has been explained very nicely. And it is a very elaborate talk, and obviously time was also very 1 hour 45 minutes continuous speaking means that is also very tough thing, but we have continued very smoothly and very elaborately. So thank you, Professor Punia, for giving your valuable time with us, and for our participants also. And I want to thank you on behalf of me, on behalf of my department, on behalf of my university, Maulana Abul Kalam Azad University of Technology. So thank you from the organizer point of view. Thank you very much. And if there is no question, is there any question? No, there is still now there is no question. So okay. If there is any question, they can ask us in future also. Participants can ask, and we can communicate it to the Professor Punia for giving necessary explanation out of it. Obviously, he is working in a laboratory which is up to date, meaning state of the art laboratory, where all the facilities are available. So I think he has also shown us some glimpse of that one, because the molecular beam epitaxy laboratory he has shown that how that beam is developing or fabricating, they are fabricating in their laboratory. And all the equipments also available, like TM, SEM, AFM, STM,
Yes.
all equipments are also available. So this is a state-of-the-art laboratory, obviously internationally famous laboratory. So that is also a facility, and obviously our university people can go and see and visit, and at least to get some idea about all the experience, how that material can be developed, and getting some idea about the theory. If they go, then it will be better to understand how things are developing, and how it can be analyzed or characterized in different steps. So thank you, Professor Punia, for giving such a nice lecture, an elaborate lecture. He started from the very beginning and end with some output, means delivery, because how device can also be developed from that, and what are the different utility of these devices. The applications area you also mentioned to some extent. So thank you very much. And I think Professor Sanal can take care.
Thank you, Professor Bhunia, for a very interesting and engrossing talk on a very exciting topic.
Also, thank you very much for giving me this honor to present our activity to such a faculty development program. I hope it will be beneficial for them, and for any use of our facility, please approach us without any hesitation. And also, if I don't know, if always before any talk, before ending any talk, I give an advertisement. The advertisement is that we are also running a synchrotron beamline facility at Indus synchrotron facility in Indore. So this is X-ray facility. We can do X-ray reflectivity, X-ray diffractions, low temperature, high temperature X-ray, and I am the in charge of this facility. And it is an open national facility, so anybody can come and use indoor RRCAT. They give the facility for travel and accommodations, and we also help in conducting experiments. So that facility also, if you want to use, welcome, apart from our lab facilities.
Okay, thank you for additional input, because that is not that is a additional facility for our students, for our faculty members. So thank you for giving that information to all participants and members. That is some additional information and additional facility that we can add in future. future, or member can add in future when they need to do anything on that type of experiment or that type of data collection. Thank you very much.
Okay, so can I leave now?
Sarnal?
Can I leave?
Sure. So I'll just contact the next speaker.
Okay, Professor Bhunia, you're tired actually. Long one and very close to 2 hours.
Next speaker is Professor Dr. Shorin Das. He has not joined yet.
Have you got him in?
No, he did not pick up the phone. I talked to him in the morning. He said he will come around 4 o'clock.
Sir, meanwhile, we can give the instruction about the quiz. So we can give the instruction about the quiz that we will be disclosing the link of the quiz at the end of the session, and the quiz is mandatory.
Oh. Sorry. Hello. Hello, তোমার কথা শুনতে পাচ্ছি। Hello, তুমি জয়েন করে রেডি। হ্যাঁ লগ ইন করে।
Dr. Sandal, Prem Kumar is asking for quiz. Whether quiz can be.
So kindly give the instruction to the participants that we will be having
at
today.
the end quiz. At the end, quiz is to be completed. That you have mentioned.
So kindly inform all the participants about the quiz and the certificates.
Yeah.
So that they can attend.
At the end of the seminar, so you can make that announcement, Mr. Prem Kumar. Why
Yes,
don't you
sir.
make the announcement?
Okay, sir. So for participants, today there will be a quiz at the end of the session. So the quiz is mandatory in order to get the successful completion certificate. So please attend the quiz, and we will be sharing link at the end of this session. So please stay with us and kindly attend the quiz. Today we are at the end of this whole FDP program. So overall feedback is also needed at the end of the talk. So please attend. Sir, sorry, sir has joined. So
Right.
Hello.
Yes.
Professor, can you hear me?
Yes. I can hear you, but we cannot see you as yet.
Okay, you want to see? Okay, just give me a minute. Okay.
Right. Now we can see you.
Okay. Yeah.
So we are happy to have Professor Shorin Das in our midst from ISAR Kolkata, and I will just introduce him. So Professor Shorin Das has done his PhD from Harish Chandra Research Institute, HRI, Allahabad in 2004, and he was a postdoctoral fellow at Weizmann Institute of Science, Israel from 2004 to 2007, and he was a research associate CHEP, Indian Institute of Science from 2008 to 2009, and then he was a postdoctoral fellow at Forschung Zentrum Jülich, Germany from 2009 to 2010, and he was a guest scientist at Max Planck Institute for Physics of Complex Systems based in Germany from 2013 to 2014. Then he joined as assistant professor in the Department of Physics and Astrophysics, University of Delhi, where he was working from 2010 to 2016, and now he is an associate professor at ISAR Kolkata from 2016 to present. So, this FDP, Professor Shorin Das will talk on topological superconductor and Majorana fermions. Okay, so with that, I leave the dais to Professor Shorin Das.
So thanks a lot, Professor Sanyal, for inviting me, and particularly welcome you back to Kolkata after a long time. It's really a pleasure. It's nice that you're back and you're kind of next door to us. What else? So let me just start. This is probably the last talk. You must be very, very tired of listening to lots of talks. I'll try to make it brief as much as possible. So as the topic says, so I should share my screen, right? So how should I do that? Share screen. Yes. Can you see my screen?
Yes.
Okay. Can you see my cursor also?
Yes.
Okay. Yeah, so play. Yeah. No, I can't see my cursor anymore. Can you see my cursor? Because for me the cursor is not visible anymore.
No.
Right now, cursor is not visible, sir.
Not visible, right? Okay, so maybe I stay in this
Now,
mode.
now it is visible, sir. Now it is.
Yeah,
visible.
I think maybe I stay in this mode. If I play the talk, I think it's kind of disturbing, so I'll just scroll it down. Okay, so I'll be talking about, as the topic says, I'll be talking about topological superconductors and Majorana fermions. So I think to do justice to the subject, what I will try to introduce is the topic of topological insulators and topological superconductors, which has been, like, a topic of excitement for us for last, I would say, 2 decades, definitely 2 decades. So I'll try to introduce the subject and what it means. What is a topology? We know what is an insulator. We know what is a superconductor, but when we address them as topological superconductors and topological insulators, what exactly that we have in mind in the present context? So that is how I would like to start. So, as I said, it's topological state of matters in which it's a very vast variety of subject. I'll be particularly focusing on insulators and superconductors, and to be more specific, I'll be talking about non-interacting topological insulators and superconductors. They are more from the perspective of band insulators and band superconductors. So really, band theory is at the heart of it when we define them as topological material. So that must be kept in mind. These are not amorphous material which we are referring to as insulators and topological insulators and superconductors. The topological aspect of it is really stemming from the fact that they're organized in a lattice. And of course, it can be generalized to also amorphous state of matter, which I think many people has been putting a lot of effort, particularly in the Indian context. I think the IISc group has been looking into it quite vigorously. Vijay Shenoy has been one of the playing a lead role in that. But I will be focusing mainly on band insulators and band superconductors. So when you look at, so let's say when you start with this topic of topological insulators and topological superconductors, the common word is insulator and superconductor. And what you have to ask is what is common between them. So when you think of insulators, probably what comes to your mind is rubber and so on, which on a daily basis we watch. And then we have these wires inside, which are really the standard metals. And if you think of how does this metal, which is a conductor, becomes a superconductor. So the idea is that if it is a superconductor, as you start cooling it down, if it is a metal, then essentially at almost as you tend to zero temperature, there's always a residual resistance which is coming from quantum effects, which you cannot kill even at zero temperature. But if it is a superconductor, at a critical temperature, you see that this resistivity suddenly drops and goes almost close to zero, and that is a superconductor. But the question is, what is common between an insulator and a superconductor? So the common thing between them essentially is the gap in the spectrum. So if you think of both superconductors and insulators being something which is comprising of electrons and electronic orbitals, then what it is saying is, as you try to excite the electron in these materials, you observe that you just cannot excite the material. There is an energy gap in the spectrum which stops you from exciting an electron, and hence if it is costly to excite an electron, you cannot really have electronic transport, because the whole phenomena of transport depends on the fact that you apply a finite bias to the system, and as you apply a finite bias, there is a driven flow of electrons. But if the electronic excitations are itself gapped, you really cannot drive this electron. They are just static. They don't move under the bias unless the bias equates the gap. So the common thing between the insulators and the superconductors are the gap in the spectrum. Now, we are talking about topological insulators and topological superconductors. So one thing we observed is that the insulator and superconductor has one thing in common, that single particle excitations are gapped out in the spectrum of both. Now, what is topology? Now, topology is a subject, is a concept, mathematical concept, which helps us group geometric objects which are connected to each other through continuous deformation. So as you can see, the donut can be continuously deformed into a cup with a single handle. If you put multiple handles, each handle you add becomes a different topological object, right? So unless you perform a surgery, you really cannot make this into something else. That's the point. So you can continuously deform one into one another, like the donut into a cup with a single handle. But if you want to open the donut into a cylinder, you have to perform a surgery. So that's topologically distinct, right? So now, if we have a situation where the insulators and superconductors are having a topological aspect associated with it, which is protected by the gap in the spectrum, we call them topological insulators or topological superconductors. So the primary point is, as long as you don't close the gap in the insulating spectrum or in the superconducting spectrum, you really cannot change the topology. That's the property of the material. So now it is important to understand what is topology here. So it's topology essentially of the Hilbert space of the problem. So in the Hilbert space, when you have, so given a problem, for example, if you think of a problem of a two-level system, then the Hilbert space is two-dimensional. It is kind of spanned by a, if I am in the SZ basis, then it is spanned by a up state and a down state, and any arbitrary state can be written down as alpha times up plus beta times down, where alpha and beta are two complex numbers, such that if the state is normalized, then mod alpha square plus mod beta square is 1. So that's really, that defines the normalizable Hilbert space of the problem. But on the other hand, when you write down a Hamiltonian, so the Hilbert space exists on its own right, it does not require a Hamiltonian. Once you impose a Hamiltonian on the problem, these states become special in terms of their energetics or in their dynamics, how they evolve in time, right? So now you can think of a map between the space of Hamiltonians and the space of states. And if this map can be either straightforward or it can be twisted. So this twistedness of the map essentially encodes the topology which is involved in this problem, right? So essentially here, when you are thinking of a band structure of an insulator, the band structure has a certain Hamiltonian, and this Hamiltonian in this respect can have topologically non-trivial properties or topologically trivial properties, and we are going to make a distinction between the two. And the point is that this distinction actually leads to really physical phenomena, which we will try to pin down, right? So that is the topology. So what one is claiming is that if we can find insulators and superconductors which has gap in the spectrum, and this gap is responsible for protection of the topological aspect of this Hamiltonian, then we call them a topological insulator and a topological superconductor. Now you automatically come to this conclusion that if I have to destroy this topology, the only way I can destroy it is by closing the gap, right? Because that is exactly equivalent to a surgery here, right? I need to do a surgery to change the topology. Now, what protects my topology in this problem is the gap. So essentially, it means that any time you are going to change the topology, you have to close the gap. It also means that if we have to make a phase transition, a normal superconductor has to go to a topological superconductor. If it has to move to a trivial superconductor, then it must first close the gap at some point, which is the phase transition point, and then again reopen it. But once the gap reopens, you know it's a trivial state. So the only way you can change the topology is by closing the gap. This statement itself has a very non-trivial consequence. So let's ask, what is the consequence? So think of this simple-minded picture where you have the first material which has a topological character of one type, which is an insulator. Then you have another material which has a topological invariant or the topological property of another type, and then you try to make a junction between the two. Now what we know is that each of these insulators independently are having a topology which is protected by the gap. So essentially we cannot really think of a situation where continuously, if I start from the left, I can continuously go to the right without closing the gap, right? Because the only way I can change topology is by doing a surgery. The equivalent of a surgery is closing the gap. So essentially it means that as you pose a junction between two topologically distinct objects, and if the topology is protected by the gap, then you are ensured, if it's a question of insulator, then you are ensured to have a metal at the boundary, right? Because a metal is nothing but an insulator which doesn't have a gap. So if you have a gap in the spectrum and you're slowly shrinking the gap and finally closing the gap, when you have just closed the gap, when the valence band touched the conduction band, you started having a semi-metal, right? It's no more an insulator, it's a metal. So that's exactly what you're going to get in the junction. So what it's saying is that at the boundaries of this material, you are ensured to have a very special metal which is protected by the topology, right? And it turns out that these metals are not only just metals, they are very special metals in the sense that they are like massless Dirac fermions. So they have properties, their description effectively in the low energy limit, if you look at the band structure, looks like Dirac fermion. So they are essentially, we know that once you have a massless Dirac fermion, the spin of the massless fermion is locked to its momentum. So essentially you get something which is a perfect metal where the spin of the electron is locked to its momentum. And you are ensured to have it, right? Because it is protected by topology. So you can think that this left hand side or right hand side, whatever I have drawn, is essentially, you can think of the air. If you think of air is a trivial insulator. But here, if you have a non-trivial topological insulator, then at the boundary between air and this insulator, you're going to get a surface state which is essentially a Dirac metal. That's the claim. So now it has different consequences in different dimensions. So if you think of a one-dimensional wire which has such a junction, you're going to get a bound state at the boundary, right? It cannot be a metal because you are in one dimension. In one dimension, if exactly there is a domain wall between two topological material at a point, you're going to get a bound state there, which is localized there. Now, if you go to 2D, then essentially at the boundary, you're going to get a one-dimensional metal. And if you are in 3D, and if you go to such a boundary, you're going to get a two-dimensional metal, and so on and so forth. Now, in a similar spirit, if you think of topological superconductors, the same thing goes, that if it is a one-dimensional topological superconductor, you're going to get a bound state at the junction. If it is a two-dimensional topological superconductor, then you are going to get I won't call it a metal. What you get is essentially a dispersing Majorana mode, two-dimensional Majorana mode, which I will define in a moment what it is. And similarly, you can extend it to higher dimensions. So that's the basic idea here. Okay. So should I stop here and take questions, if any?
No, we can take questions at the end.
Okay, fine. So, okay, so the importance of such research is multifold. this new class of 1D and 2D materials are Dirac materials, which are robust against disorder. So maybe I need to spend a few minutes explaining what we mean here. So most of the time, these topological band structure are associated with certain symmetries in the problem, which are usually anti-unitary symmetries. In this case, most of this material which are discovered recently, their topological properties are protected by time reversal symmetry. So these metals essentially respect time reversal symmetry, which means that if you do not break time reversal symmetry, these metals are pretty robust. So when you say spin momentum locked, you can think of it this way, that if you have an interface and if an electron is coming in and it bounces back, then its momentum k has to go to minus k. But it also means if the spin is locked to the momentum, if the momentum is this way and this is the spin, if it goes here, then once the momentum flips, the spin also has to flip, right? That is what is the essence of spin momentum locking. So if this is the direction of motion and this is the spin, when it comes and bounces back, it has to do the flip. Now, where will this extra momentum go if there is nobody to absorb this momentum of the electron? Because the electron is coming with spin up and it has to go back with spin down. So one unit of angular momentum has to be absorbed by somebody. So essentially, if you do not have magnetic barriers, there is no way you can absorb this momentum, which basically means you cannot backscatter. So exactly backscattering, exact direct backscattering, head-on backscattering is something which is badly suppressed in Dirac metals. So that is what makes them a very good candidate for doing all kinds of building circuits of quantum electronics and so on. Because backscattering, once it is engineered properly, backscattering can be heavily suppressed. And this argument can also be reduced to a Berry phase argument, which I don't want to get into now, but it essentially says that if you think of a 2D Dirac material, it has a circular Fermi surface and the spins are locked everywhere to the momentum. So if you go once around the Fermi surface, it picks up a Berry phase of pi, and this Berry phase of pi really gives it a solid robustness to backscattering. Now, it also has nice spintronic applications, because spintronics is nothing but flow of spins, and because the spin is locked to the momentum, as you kind of twist and turn the momentum, you can actually control the spin of the electron, which is a unique opportunity. So if the spin is locked to the momentum, you don't really independently control the spin of the electron. By guiding the electron in a certain way, you actually guide this spin of the electron. So it's very advantageous for performing spintronics operation. So that's one kind of advantage of these Dirac materials. On the other hand, when you think of these Majorana fermions, they are also very interesting material. So let me I'll come to this point as I proceed, but just to tell you that they have very strong implications for topological quantum computation and for formation of topologically protected quantum qubits. So that is where Majoranas are supposed to be very, very useful, and also they are classic examples of non-abelians. In a sense, in 3 dimensions, we know 3 and higher dimension, we know that the statistics of a particle is either quantum statistics of a particle is either fermionic or bosonic. But if you are in 2 dimensions, 2 dimensions being special, you have possibilities in which you can have anyons which are neither fermion nor boson. And these examples really can be found in nature in experiments nowadays, because these Majorana particles exist. They are one of the examples of a non-abelian. So I'll try to explain this point a little better as we move ahead. And they have so from the point of view of being an exotic particle, they have a lot of importance, but also they're important for application as far as quantum computation is concerned. So that's the importance of these guys. Okay, so let's move ahead. Right. So what I will do in this talk is I will try to introduce you to the concept of Majorana fermion via a model which is given by Kitaev. It's one of the really simplest model where you can see what a Majorana fermion is. It's very, very easy to appreciate what this object is. All other models are extremely complicated, but this Kitaev chain model is really beautiful, and it puts forward this idea that what the Majorana fermion is. And now following Kitaev's, actually Kitaev came up with this paper I think in 2001, and after that within I think 9 to 10 years people came up with experiments in quantum wires where they could see that such Majorana fermion exists and saw signatures of it. Then in the next part, I'll try to connect this to quantum Ising model. So I'll try to connect this to some sort of ideas of phase transitions, because in the Majorana chain, you have a topological phase transition. One of the classic examples, solvable example of phase transition is really the quantum Ising model. It's very easy to solve, but it really gives you beautiful insight about phase transition, and there is a very close connection between the Majorana chain and the quantum Ising model. In the Majorana chain, you essentially have a topological phase transition. So when I say topological phase transition, it basically means you can define an order parameter in the problem which is purely non-local in nature. It has nothing local about it, right? Because it is topological. That's the whole idea. It's not geometric. It's topological. What matters is the entire object. Its local informations are not important. What is important is its global structure, right? Does it have punctures or it doesn't have punctures, and so on. So your order parameter is something which is spread all over the place. But when you think of something like quantum magnetism and you think of the quantum Ising model, your order parameter is something which is local magnetization. You are trying to ask question about that, and when it picks up a finite expectation value. So there is a connection between this global order parameter, which is a topological phase transition, and this local order parameter, which is this Ising model, which undergoes a standard second order phase transition. So I'll try to make a connection between the two. Actually, this model can be completely mathematically mapped onto this model, the quantum Ising model, and I think that's really beautiful. It gives you some insight about this problem, because the way you solve the quantum Ising model is by actually mapping onto Majorana fermions, but this mapping is a non-local map. So essentially you take they take these spins which are local in nature, and then you map onto fermions, which in the spins language is a very non-local object. And when you put the two things together, you see that it gives you a sense that why one of them is topological while the other one is really a standard second order phase transition, because your mapping was non-local. Whatever was a local order parameter became a non-local order parameter and became a topological transition, a topological state of matter, right? Then we have, I'll talk about experimental signatures of Majorana fermion in transpose setup. I'll tell you at least some, I'll show you some slides about how the experiment is set up and what all has been observed and how sure we are that we are really looking at Majorana fermion at the moment. And then if time really permits, I'll tell you very briefly about what are our efforts, maybe one paper in which we have put in some efforts in this direction. Okay, so let's move ahead. So the idea is the following. So Dirac versus Majorana fermion. So when you think of Dirac fermion, I'm not thinking of really from a particle physics point of view. It's more from just simple standard condensed matter point of view. If you're familiar with second quantization, you know that when you have fermions, we have creation operator for fermions and we have annihilation operator for fermions, and they follow this anti-commutation algebra, which is the anti-commutation, which tells you that you really cannot create two fermions with the same quantum numbers, right? So, and it also tells you that C Dagger square and C square is 0. That's exactly the statement, that you really cannot create two of them with the same quantum number, because of which these squares are 0 and the anti-commute that ensures also the same property, right? So now what we can do is just a small mathematical trick, that we take C's and C daggers and we rewrite them in terms of some operators which are Hermitian. So C and C daggers are of course not Hermitian, they are Hermitian conjugate of each other. If you dagger one, you get the other. But I can write two new operators where I write C as eta plus I eta bar by 2 and C dagger as eta minus I eta bar by 2. And you notice that when I invert these etas to write in terms of C's, you will see that both eta and eta dagger are actually Hermitian objects. So what I did, I essentially, if you think that C is an electron creation operator, what I did is I fractionalized the electron into two Majorana fermions, one of type eta and one of type eta bar. Notice that the eta bar comes with an I, which basically means that if I define some sort of an anti-unitary operation, which is more like a time reversal operation, then this goes to minus of itself. So eta and eta bar has different different transformation properties under some kind of an effective time reversal symmetry operation, right? So these are, so essentially this is some sort of, so you can think that this is mathematically, this is just like changing of basis. You could write a problem where you are solving a problem, you write everything in terms of standard fermionic operator, then you say that I don't like them, I want to change basis, I want to write it in terms of something which is Hermitian. You could do that, and that is eta and eta bar. You can just re-express every Hamiltonian which you have seen in the past in terms of which are made out of fermions in terms of these guys, right? And you see that they also follow an anti-commutation relation. So they are fermion in nature, but they are real fermions. So you see the essence of the story is they are their own antiparticle. In a sense, you see eta is equal to eta bar is telling you they are self-conjugate, they are real. So they are their own antiparticle. So that is special about them, right? So now, I mean, we can always do all kinds of mathematical transformation. The question is, does it have a meaning? When we ask this question, that does this thing has a meaning, what we mean is that if we perform an experiment, can I individually address one such excitation? If I can do that, I will call it physical, I will call it meaningful. If otherwise, it just remains as a mathematics. And that exactly was the genius of, I think, Kitaev, that he realized that you can address one of these particles individually at a time, and you can energetically separate them out from the rest of the spectrum. It's like saying that you have a gap in the spectrum, there are excitations here, there are excitations here, and what sits inside the gap as an isolated guy is one of these excitations which are of Majorana type. So if you could do that, of course it tells you that experimentally you can address this guy while nobody else messes with you. So you can really individually find them. And once you can individually find them, it becomes physical. Of course, it's no more a mathematical trick, it really is the truth. So now let's take the simplest possible Kitaev model, which is this, just a 1D tight binding model with a superconducting correlation. So maybe I just want to make one more comment here. So how would you make something like this? What it is saying is that it is a 50% electron, 50% hole. So when Majorana in his original paper was really looking for these Majorana solutions in the context of particle physics. So in the context of particle physics, if you think of the Dirac equation in 3 + 1 dimension, 3 space 1 time, then you know that you get these gamma matrices. And gamma matrices, you cannot, so the gamma matrices in general are complex. So essentially the Dirac equation is a complex equation. So you really don't expect that the solutions of Dirac equation can be real. But Majorana discovered this point, that there is a special representation in which you really can have pure real solutions of the Dirac equation, and they essentially represent a particle, a new kind of particle, which is its own antiparticle. So it doesn't, when you have fermions, you have antifermions. When you have electron, you have positron, right? You always have antiparticles in particle physics. But then he predicted from this solution of Dirac equation that if you have such solution, it essentially implies that you should have a particle in nature which is its own antiparticle. And then there was a lot of speculation that probably the neutrino is one of the particles which is its own antiparticle, which is yet to be confirmed. There is something called a double beta decay experiment where people are expecting that they will be able to pin this down, but this is still not resolved. And so as far as particle physics is concerned, it is still an open question, that does Majorana particle exist as a fundamental particle or not. Now if you come back to condensed matter physics, we have to ask this question, what is a 50-50 superposition of a particle and an antiparticle which can become a particle which is its own conjugate, right? So you have to ask this question first, what is your vacuum? Because in particle physics, we know what is our vacuum, a zero particle state, which Dirac gave an interpretation that it is like a filled sea of positron and then a vacuum above, right? No particles above, and then as you excite, you generate electron-positron pairs. So the equivalent of that in condensed matter physics is really the filled Fermi sea. So you can think that the vacuum of the particle physics is now being replaced by the filled Fermi sea, and the excitations you can have on the filled Fermi sea is essentially some sort of particle hole excitation. If this is all the electrons are filled here, if you take out an electron from here and put it there, then you leave behind an absence of an electron which you call hole. So now what we are expecting is to create a superposition of this whole state, the absence of an electron and an excited electron in a coherent fashion, such that they're exactly 50-50 superposition. It's not any arbitrary superposition, it's a 50-50 superposition. So if you think of mean field superconductivity, and you know that we kind of solve these superconducting Hamiltonians and diagonalize it using Bogoliubov transformation. If you look at Bogoliubov transformation, that's really looks something very much like this. It is a superposition of an electron and a hole. Now, what you will never find in a garden variety superconductor is that you will never find a superposition for any parameter space where it's exactly 50-50. That is exactly what you do not get. That is why we never saw these Majorana fermions in the past. We never paid attention to this question. That can we have a superconductor where we get a state where the electrons and holes superpose exactly in a 50-50 fashion. And that was the genius of Majorana. Majorana put forward a model where this 50-50 superposition could be generated as a topological bound state, as I said here, that what you can have, if you have a one-dimensional superconductor here, then what you're expecting is exactly at the juncture a bound state to evolve, which has this property that it is a 50-50 superposition of an electron and a hole. So that's what one is trying to arrive at. Okay. So now let's look at the model. So this is Kitaev's model. So what we have is a one-dimensional chain. So it's a 1D chain, and for each site, the sites are kind of labeled by I, and each site has a creation and an annihilation operator given by Ci and Ci dagger. So as you see that the first term is nothing but the chemical potential term. It's the number operator on that site times the mu, which is the chemical potential. For convenience, we have put a factor of half here, and then you have the hopping term, which has a strength W and it's only nearest neighbor hopping, and then you have the term which is the pairing term. Note that because we have spinless fermions, and it's very crucial that you take, so I think this was observation of Kitaev, that you need to have spinless fermion superconductivity. So if you think about it, you'll find it very counterintuitive, because how will I make something spinless? So superconductivity and spinlessness do not go hand in hand in the following sense, that if you have electrons in one dimensions, the only way to make it spinless is you put a very large magnetic field, you open a Zeeman gap, and then you can say that I'm going to work only at this energy where the down energy guys are completely out of the game, or vice versa, and effectively you can generate something which is spinless. So it is really an extreme limit where you put very large magnetic fields and then you start thinking about the problem in a spinless language. But that's really problematic, because if you do that, you're going to kill superconductivity anyway. Superconductivity and magnetic field do not go hand in hand. Now, but it's important to have this, because what you need is not an S-wave superconductivity, but a P-wave superconductor. That's what you are looking for. You see the pairing term here, because you cannot have two electrons at the same site. You must have pairing between an electron at ith site and an electron as I plus 1th site. So that's why we have this operator Ci dagger, Ci plus 1 dagger. Now if you Fourier transform this, it is like saying that you have Xi dagger at position x times Xi dagger at position x plus delta. So if you expand it in delta, the term which you are going to get is del of Xi, right? The leading term will be something like del of Xi, which is telling you if you go to the Fourier space, your order parameter delta will have momentum dependence, right? And that's exactly the crucial element. Your order parameter should be momentum dependent, right? So if you have Xi dagger at position x, Xi dagger at position x plus alpha, you expand Xi x plus alpha about x, then you see you get a derivative of Xi, and as you Fourier transform it, you're going to pull down a k, and in the momentum space you will see this order parameter is momentum dependent. And that's exactly the crux of the matter. What you need for topological superconductivity is an order parameter which is momentum dependent. Okay. Now if you look at the symmetry of the problem, then you see that the initial problem, if you strike out this pairing term, has a U1 symmetry, right? So if you take a Ci and transform it to e to the power I theta times Ci, where theta can be any phase you like, then this is a symmetry of the original problem, right? And this essentially implies that number is a conserved quantity. You cannot create or annihilate any number. But as you switched on the last term, which is this one, essentially you broke the U1 symmetry into a new symmetry, which is a Z2 symmetry. Essentially it is saying that you don't have all the freedom which you had before, you only have a freedom that you have, so you can C can go to minus of C, and the conserved quantity now is not the number operator but the parity of the number operator. Essentially what is conserved is what is even and what is odd, and that makes perfect sense. You see, your initial Hamiltonian was number conserving. Now you said that I'm going to switch on an operator which can create particles in pair or annihilate particles in pair, which basically means if I start from 3, you can create or annihilate, make it 5, make it 1, but what you cannot make it is 0, right? So you cannot go to the even sector. On the other hand, if you start with the ground state which has 4 particles, you can make it 2, you can make it 0, but what you cannot make it is really 5 or 3 or 1. So essentially now what is a conserved quantity is the parity operator, which is -1 to the number operator. So if it is even, it is 1, if it is odd, it is -1, and that's the conserved quantity. So essentially you can separate out the Hamiltonian into 2 blocks which are block diagonal. One is the even parity sector, and other is the odd parity sector. And that's exactly the essence of this Z2 symmetry. So once you have that, then what you are going to do, because we want to see that really can we get Majorana fermions as the excitation of this problem, a true excitation, an eigenstate. So what we desire is the following. What we want is, we want to write down a problem where this operator here eta and this operator eta bar should appear as an eigenstate of the problem. That is what we are heading at, and that's exactly what Kitaev gave us. So if you look here, then the first term, so I'll just go back. You see that there is this chemical potential term. I'm going to write this term in terms of Majoranas, this term in terms of Majorana, everybody in terms of Majorana. Re-express the whole term, but remember that this was the chemical potential term, this was the hopping term, and delta is the pairing term. So if you go back and do that and write everything in terms of Majorana, the new Hamiltonian looks like this. So you have this chemical potential term which is talking to the local Majorana. So each electron here now has become an eta and an eta bar. They still carry this index I, it says the local index of the electron, right? So each of this electron has now become a doublet. You see, this is this doublet. Each of them is a doublet. Now the first term, which is the chemical potential term, is essentially binding this eta with this eta bar. That's what it is doing if we think in terms of Majoranas. Now look at the next term. So next term is eta bar I, eta plus 1. So if you look at the next term, it is trying to hold hand like this. It takes the last eta bar of the electron and connects it to the next electron's eta, and so on and so forth. This is a pattern of holding hands. If you look at the last term here, which is minus W plus delta, this is a different pattern of holding hands. So you see, it holds hand like this. It takes the first electron's eta and connect it to next guy's eta bar, right? So it is a different kind of holding hand, right? Now, what we observe is that if you put mu equals to 0 and if you put delta equals to W, then you see this term goes away, the last term goes away, the first term goes away. What remains is only one kind of holding hand, right? I'm putting mu equals to 0 and I'm also putting delta equals to W. If I do that, the last term is gone, the first term is gone, I have one kind of holding hand. So if we focus on that, what you observe is that we exactly got what we wanted. So this is that situation where W equals to delta, which is greater than 0, mu equals to 0. You see, this first electron, its eta on the boundary is left free, left alone. It's not a part of the Hamiltonian anymore. The next eta bar is holding the hand of the next eta, and eta bar eta and so on, and the last eta bar is also left alone. And that's really telling you that this eta and that eta bar are two eigenstates of the Hamiltonian with zero energy, right? It costs you no energy to have them, right? That's why they are out of the Hamiltonian, because there is actually a plus 0 here, and that's exactly the zero energy state. Now this was a superconducting Hamiltonian, so you know that if it is a superconducting Hamiltonian, if I diagonalize the Hamiltonian, there is a gap, there is a spectrum up here, there is a spectrum down here, there is a gap here, and at exactly the center of the gap is what is zero energy, right? And what one is saying is that in this Hamiltonian, in this parameter space, you have an eta and an eta bar eigenstate which is sitting exactly in the middle of the gap, right? So it is a subgap state. It is special because it sits at 0, it costs you nothing, and it is topological. You see that it really sits on the boundary. Right? So it's a non-local, so it created a non-local state, right? This eta and this eta bar created. Why am I saying this is a non-local state? Now we'll try to analyze this. what is non-local about it? There's something very beautiful about it, that it's telling you that if I make a change of basis in such a way that I identify a new fermion, which is a linear combination of the first eta and the last eta bar. You see, I had transformations like that, right? Remember? I could write, I can always make a change of basis, right? And express these linear combinations of pairs of eta and eta bar in terms of some fermion. So it's telling me, the message here is that if I create a fermion state using eta and eta bar, that is a single fermion state which sits at 0 energy and lives non-locally. Okay? It's a single fermion state which lives totally non-locally, sits exactly at 0 energy, and it's topologically protected because no local perturbations here can disturb this state. So it has two messages inside it. First message is, notice that what I generated is the 0 energy state for a fermion, which is non-local in nature. But once you have a fermion state, you can ask this question, is this fermion state filled or empty? That's exactly the two parity sectors. If this state, because everybody else has paired up, there are no unpaired guys left anymore. The only guys left is essentially what is sitting in the middle. That guy can be filled or empty. So if you fill that 0 energy state, you are in the odd parity sector. If you unfill it, you are in the even parity sector. So it's telling you that this ground state, if you think of the ground state of this Hamiltonian, this many-body Hamiltonian, is twofold degenerate. That's exactly a consequence of the Z2 symmetry of the problem. It has twofold degeneracy. And this twofold degeneracy belongs to two states which are having different parity. They're completely of different parity. Now you can also, now from the quantum computation point of view, when you start thinking about it, you realize that this is nothing but a two-level system. Because being empty is one state and being filled is another state, and that gives me a two-level system. But this two-level system is very beautiful because it is non-local in nature. No local perturbations is going to destroy my information if I encode information on this non-local fermion, right? It's not a local fermion that local perturbations will take away this information. So that's exactly the relevance of this as far as quantum computation is concerned. Now from the phase transitions point of view. Now so think of ferromagnetism. When you think of ferromagnetism, what happens once you go below the transition temperature? Initially, your spins were pointing in all possible directions and it costed them nothing. Now, at some point, they all want to point in the same direction, but they really don't know which way to point. It could be any direction. But of course, the system has a degeneracy in all possible directions, but the real system will spontaneously break this symmetry and choose one. In a similar sense, this guy will also spontaneously break the symmetry and choose either the even parity sector or the odd parity sector. Right? There is a spontaneous symmetry breaking. So here there is a spontaneous symmetry breaking, but there is no local order parameter. The non-trivial thing in Ising model, or the trivial thing in Ising model, is there is a local order parameter which spontaneously breaks this symmetry. Here there is a non-local order parameter which spontaneously breaks this symmetry. So that is the topological essence of this phase transition. So I think I kind of went through all these points here, and the other thing which is slightly more technical, but it's interesting, that if you imagine that you have a soup of these Majoranas, that you have not just one pair, you have many such pairs, then you can imagine that each being at 0 energy, you essentially generate a state which is heavily degenerate. It's a heavily degenerate state, right? If all of them, you have a soup of 0 energy fermions. Of course, because my starting point is electron, I really cannot generate odd numbers of such guys. I will always have them even, no matter what. If nature creates them, I know that the fundamental starting point is electron. So essentially, if I get these 0 energy solutions, they will always come in pairs. If somebody tells you you have one of them, you definitely don't believe him because he doesn't know where the other guy is. They always come in pair. They might be non-locally distributed, but they will come in pairs. Now, if you take a soup of them, these are fantastic objects because they are no more standard fermions. They are what we call the non-abelian anyons. And why do we say that? That what you can do is you can take these Majorana fermions and exchange them in 2 dimensions and take one around the other. Right? You can do this operation. Now, it's like doing, if you know the concept of Berry phase, we know that if there is a wave function if there is a wave function and you adiabatically deform some parameter of the problem such that the parameter come back to itself, then you know that the wave function comes back to itself up to a phase, right? That's exactly Berry's prediction, right? If you have a wave function which is sitting on some Hamiltonian which has certain parameters, and you deform the parameter of the Hamiltonian in such a way that the parameters in the parameter space forms a loop, the wave function does come back to the same wave function but up to a phase. But if you have a degenerate subspace, and when you perform this operation, what you cannot ensure is transition between degenerate state, because that costs you nothing. It's free because it's degenerate, right? So if that such transitions happen, this Berry phase becomes a matrix valued phase. It's not a simple e to the power I theta, it is actually a e to the power I, a matrix sitting there. And you can imagine that an operation in which I take the first and take the second guy around and I do the reverse, they need not necessarily commute. These are non-commuting operations. So you get fractional statistics for these guys, but these are not only fractional statistics, they're also non-abelian statistics. They follow, because of this degeneracy, they follow non-abelian statistics. And these non-abelian statistics can be used for encoding information, doing quantum information processing, writing codes on it, and so on. There's a very nice topic which is kind of coming up these days, and a lot of people are discussing it. This is called Majorana surface codes, which people are trying to essentially engineer this Majorana on the surface and trying to see how you can do gate operations to perform, to run certain codes written on the surface, which can do quantum computation. Okay, so that's the other aspect of Majorana which is very important and very exciting. Prabhuda, should I stop here and take questions?
No, we'll take them at the end.
So how long have I been speaking? So am I done, or how much time do I have?
No, you have about 1 hour almost.
Another 1 hour? Oh, I see.
I mean, at best. I mean, you can stop
No.
before that, but
No, I don't want to burden people. I think, okay, so I think,
but at
yeah.
least, but at most you have 1 hour.
Fine. So I'm not pressing in time. Okay. So now I think the point really to be stressed here is that these topological aspects, when you think of these topological aspects from the point of view of tight binding Hamiltonian, you really have to pay attention to what is the unit cell. And I'll try to demonstrate here what I mean by that. What is the fundamental, essentially it's like saying that what is your fundamental unit which you do not want to break, and your topology is completely defined around that cell which you do not want to break. That is why there is a topological aspect to the problem. And to make it well defined, so let me put the following. You see, what I've done here is that I've taken the chain, and this was a trivial chain, remember? So let's go back. So we were in this situation where I have only the chemical potential term and everybody else is not there. So all you have is the local electrons, and then you have pairing up of local electrons. These are all local electrons, and the local electron, inside the electron you have a pair of Majorana, they are holding hand, and nothing interesting is happening. Now imagine that I gave you this freedom that you could throw away Majoranas in pairs as you desire. If you could do that, what you could do is you take this last guy, this eta, and throw it away out of the game. You take this last guy eta bar and throw it away out of the game. If you do that, you see this becomes a topological object, because now what you have got is an end state. Everybody is holding hand. One guy is free here, another guy is free here. So if you could do that, you really did not need anything non-trivial. You will say, I can just break this electron, take this guy and throw this away. But that's exactly a nuisance. That is not something you can do, because we know our fundamental starting point is that electrons are composite object. You really cannot break them and take a single electron and break one Majorana and throw it out of the game. This is something you cannot do, right? So what I'm trying to say is that this is a unit cell of my problem. I'm not going to disturb this unit cell ever. So if I do not disturb this unit cell, so that's exactly the point I'm trying to make here. If you could throw this guy and this guy away, you would say this is also a topological state, and then I will have no statement what is topological and what is not, because everybody looks the same as far as I can take two guys from the end and throw it away. The main point is that there are certain things which you can break and certain things which you cannot, and that really gives you this topological classification. Otherwise the classification itself breaks down and it's totally meaningless. In a similar spirit, when we found the topological phase, it was this one, right? Now again, in this phase, everybody was holding hand except for the last two guys. Now if I am allowed to break the electron and take this last guy here and take this last guy, throw it away, then this becomes a trivial state. Everybody is holding and there's nothing special about it. So I'm not supposed to do that because I'm not supposed to break a single electron and throw things away. Right? That's really important. Though you would think that that's allowed, because after all, you're taking out something which is like an electron. So it's not bad, very bad thing to do. Right? Of course, you should not have odd number of Majoranas. That's absolutely absurd. You don't even have a well-defined Hilbert space. But even when you have things in pairs, it's not that you can take away anybody you desire, any pair you desire. You have to take away something which is a composite electron if you want to take things out of this system. Right? So that's very important. You need to respect that. And only when you respect that, you see that there is something interesting in the problem. There is a topological aspect to it. So unit cell is very important. When you will carry this forward, same idea to topological insulators, you will see that this physics will come from the unit cell of the problem. So now we can define, so all I have been saying all this while is that there is something topological, there is something topological, but essentially it means that when you have to define something like an order parameter, some mathematical quantity which quantifies what you mean by topological. So you have to define what is called a topological invariant, which kind of, you define a mathematical quantity which kind of quantifies this object such that as you deform it, unless you create a puncture, the number does not change. Right? You need to define a mathematical quantity quantitatively such that that number is such that it kind of says that this is this surface which is closed in this fashion, and unless I do a surgery on it, I can do whatever deformation I like on it, this number is not going to change. So you have to define topological invariants. That's the point. So in this problem, you can define a very simple topological invariant, which is essentially a winding number. So I'll try to define what is a winding number here. Essentially what you can do is you can take the Hamiltonian and expand the Hamiltonian in momentum space. If you do that, you will see that the Hamiltonian will always comes like a two-level system. So you have this composite blocks for each k and minus k, you can write a two-level system. So it's like you discretize the whole problem in terms of hierarchy of k's and minus k's. So k equals to minus 5, k equals to plus 5, k equals to minus 4, k equals to plus 4. If you discretize it that way, the whole problem breaks down into problem of individual k's as long as momentum is a conserved quantity. Right? It's like hierarchy of these blocks. So I can focus on an individual block, and what I see is that if you have a 2 cross 2 Hermitian Hamiltonian, you know that you can always expand such a Hamiltonian as identity plus b dot sigma, where you can define an effective two-level system. So this Hamiltonian here for a specific k level becomes nothing but a spin half problem in a magnetic field, where the magnetic field has to be identified with this bk, where bx is 0, by is minus I times delta tilde k, and bz is ek. Right? That's the identification. So important point to note here is that this spin or this magnetic field lives in 2 dimensions. Right? So if you have to define winding number, as I will go to the next page, you will see it's very important that you have 2 dimensions. You don't live in 3 dimensions. Then you cannot define winding number. Winding number is something which is a 2-dimensional object. You need to have a singularity, and it's asking, without crossing the singularity, how many times you are going around the singularity. This question becomes irrelevant as soon as you can lift the curve above the surface. Then it's meaningless, because the singularity really lives in 2 dimensions. So it's a meaningful question if you have a puncture in the middle in 2 dimensions, you're going round and round about it without lifting yourself from the 2-dimensional space, then it's a topological invariant. That how many times did you go around the singularity? That's exactly the invariant here. So it's important that this is a 2-dimensional object. And now if we go to the next page, next page, what I have done here is that I have gone, so I need to make one more point here, sorry. So note that I am in the momentum space, and because I am in a lattice, my momentum really runs from minus pi to plus pi. It's not minus infinity to plus infinity, because in a lattice you have a smallest scale in the problem, which is the lattice spacing. Your largest momentum in the problem is proportional to the inverse of the smallest length scale in the problem, which is a. So essentially pi over, I have put the lattice spacing to be 1 here. So your momentum goes from minus pi over a to plus pi over a, right? So and the ends, so the minus pi over a and plus pi over a are points which are kind of the same. They represent the same point, right? They're periodic. Okay. So the momentum space on a lattice is essentially periodic. They are the same point. So essentially the momentum space forms a ring. It's a 1D ring, right? So now what we are going to do is look at the evolution of this vector bk which you have defined in the two-dimensional space of bz and by as we go around once in the momentum space. That is, we go from k equals to minus pi to k equals to plus pi. What you see is that when you are topological, then this vector actually has a trajectory like this, which actually takes the origin at the inside the circulation. Okay, and when it is non-topological, then you see the circulation is such that it does not have the origin at the center. So it basically means if you calculate this winding number here, in one case theta will wind by 2 pi here, here it will just wind 0, right? So in one case you have a finite winding number, in the other case you have a 0 winding number, and that gives you a distinction between the two, which is topological in nature, which is independent of how you could deform this trajectory. As long as you live in this space, you never touch this origin, you keep away from it, you can deform it whichever way you like, make it wiggly, but this topological invariant will stay 1 and nothing will happen to the Majorana, it will stay put. Okay? And in this case, the Majorana is not there. The winding number is 0. So that is the topological invariant which you can associate with this problem. There is also a Z2 topological invariant, but maybe I'll try to skip that. It just gets more complicated. Now a connection, I think this is a very nice article where they made a connection between the Ising model and the Majorana chain, and this is what I was hinting at, that essentially what is a second order phase transition in the Ising model becomes a topological transition in the Majorana model. It's one of the most beautiful, solvable, very simple Hamiltonian, very simple problem which you can solve and see for yourself that really a second order phase transition with a local order parameter goes over to a topological phase transition where there is a one-to-one mapping between the two problems. Of course, you have to kind of build your dictionary very, very carefully, but if you do that, you will see that there is a direct connection between the two. Now, I think before I go ahead, so I don't want to get into that, I want to tell you definitely about the experiments. So experimental signature, what has been observed in an experiment is of course very important. So motivated from whatever was predicted by Kitev, there are a lot of leading groups in the world which tried really coming up with an experiment which could probe such a Majorana state. So before we get there, I would like to tell you one important ingredient which you must keep in mind as you are thinking of such material and such topological aspect of this problem. So what is that? So that is spin-orbit coupling. So it turns out that spin-orbit coupling breaks SU2 symmetry, but it respects time reversal symmetry. It turns out that all this topological material essentially, which are topic of research nowadays, are coming from strong spin-orbit coupling. Now, what is the role of this spin-orbit coupling is really one of the interactions which really puts relativistic effect. And we said that the surface states are Dirac fermions, right? So we saw glimpses of particle physics in condensed matter physics in terms of surface states, and actually their origin is also relativistic in the sense that you really need a very strong spin-orbit coupling to have these topological insulators in place. So the gap which I was talking about, the insulating gap of these materials are really due to spin-orbit coupling and not something else. So the band structure, if you look at the band structure, the gap in the spectrum where the Fermi level lives, which makes them an insulator, is a spin-orbit gap. Now, why spin-orbit coupling is important? Why is it that they make topological insulators? There is one, in a kind of quick way of visualizing that would be the following. That imagine that you are really creating a solid by hand. So what will you do? You will take atoms, and let's say I'm in one dimension, so I'll organize atoms one by one, and each atom, let's say, has exactly few orbitals. So you would think that if your atom has a s orbital, so when you think of a hydrogen atom, like it has an electron in the S, then P, then so on and so forth. There's a hierarchy of levels, and let's assume that there is no spin-orbit coupling. Then you would imagine that once you put this hydrogen atom next to each other in a lattice format, then this S band of this guy will talk to the S band of next guy, will talk to the S band of next guy, and open up a S band for you. The next P will, the p orbital of the first hydrogen atom will talk to the p orbital of the second, to the third, to the fourth, and open up a p band for you, and so on and so forth. So what you have a very specific hierarchy in mind as you are thinking of what kind of band structure will open up as you take this material and put them in ordered in an ordered lattice, right? Now, so which means that the natural ordering, the simple insulator has an ordering where the s orbital comes first in energy and then comes the p. Now imagine a material where the spin orbit coupling is extremely strong. It is so strong that it inverts this structure, and what happens is that the s orbital goes up in energy and the p orbital comes down. Then you know that there is a band inversion, right? What was the normal order has now become the inverted order. And it turns out that these are the materials which has completely inverted ordering of orbitals as far as energy is concerned due to spin orbit coupling are topological insulators. And as you make junction between these guys, of course you can imagine that the band has to close somewhere and then reopen. That is where you find the metal. Okay? So it makes perfect sense, and you would also imagine that these will require heavy elements, right? Because if you want to have large spin orbit coupling, you better deal with heavy elements. So if you take heavy elements like bismuth and so on, and then produce lattice structure out of it, solids out of it, band solids out of it, then you hope that you will see topological manifestation of matter there, right? So that's the idea, right? So that's the basic idea when you start thinking about engineering such material. So let's see what people engineered for these Majorana fermions. So if you think of this Majorana fermions, they essentially had indium antimonide nanowires. So people were growing nanowires, right? So here this is the engineering. So please pay attention to this picture, that this kind of reddish looking thing, this in between is, which is kind of molded by various things. This is the nanowire, right? So this object here. So by itself is definitely not a superconductor. So what you're going to do, this has a very large spin orbit gap material, and what you're going to do is put aluminum on top of it to induce superconductivity into it. So that's what is being done. You see that this long wire, you have put contacts here, there are contact pads here, which are gold contact pads here, and then what you have put on the long side of the wire is essentially a superconductor, which due to proximity effect is going to induce superconductivity into the nanowire. Then you have a super gate here, what they call the super gate. Essentially idea is that if you put negative electrostatic potential there, it's going to push the chemical potential of this thing up and down. So you can charge it or discharge it. So you can you have a control on the chemical potential of the nanowire. That's what this gate does, right? So you have the superconductivity coming from a standard garden variety superconductor due to proximity effect. You got this spin orbit coupling because you took a material which is strongly spin orbit coupled nanowire, you have put a gold contact, and then what you are hoping is that between this superconductor and this insulator somewhere you localize a Majorana fermion. Okay, that's exactly what you're hoping. You expect to see a Majorana fermion here. And what will be the signature of Majorana fermion? The signature would be that from this gold contact, if you try to inject electron into this superconductor, you will see perfect and ray reflection, which will give a conductance of 2 squared over h. I'll try to elaborate a little bit more on this aspect, that what is yeah, so I think I need to tell you about this and ray reflection process. So what you have is when you have a superconductor, you have a gap in the spectrum. So the Cooper pairs live inside the gap, and above these and below this are the quasi-electrons and the quasi-holes live, right? So now if you send in an electron inside the gap, of course the electron being not a Cooper pair, so only guys who can enter here are Cooper pairs. They are free to enter. But for electron, there is a gap in energy. When the electron comes in at above the Fermi level, what it can do, it can pair up with another electron below the Fermi level, so it becomes a pair, and then jump into the superconductor. Once it jumps into the superconductor, it leaves behind a hole below the Fermi sea, and that hole bounces off and gives you a hole current. So essentially what is happening is you send in an electron current. In response, what you get due to ray reflection is a hole current going off. So essentially whatever current you sent, it kind of doubled up, right? That's what you will see. If it is a perfect ray reflection, imagine that there is a perfect junction, there is no disorder, a perfect junction between the superconductor and the conducting metal, right? Then when you send in electrons, if the incident current is I, the current is going to double up because of this pairing mechanism. This electron will come, it will pair off with an electron below the Fermi sea, it will jump into the superconductor, a hole will bounce off. This opposite going hole current is exactly equivalent to an ingoing electron current, so I plus I is 2I. So you're supposed to see a peak. And this peak, because you are in one dimension, we know that the maximum conductance it can show a single channel, quantum conductance of a single channel, perfect single channel is E squared over H. You have got an electron perfect channel and a hole perfect channel, so the total conductance is 2E squared over H, right? So you essentially expect at zero energy, because there is a Majorana at zero energy, you expect a conductance peak of 2E squared over H. So that was the hope which one had from the experiment. When they did, there were 3 leading groups which were doing this experiment. One was the group from Covenhaven's group, I think from Netherlands, and then there was a group from Duke University, I think, and then there was a group from Weizmann Institute, and where I think Anindo Das is in IISc right now. He was one of the lead person leading this experiment from Moti Heiblum's group from Weizmann Institute. And all these 3 groups, what they saw essentially in this geometry, roughly this geometry, they essentially saw such Majorana peaks. Okay? So essentially they saw some peaks in the conductance close to zero energy. But honestly speaking, this has been a very controversial subject, and there has been enormous amount of research on are these peaks really Majorana peaks, or there are spurious sources, many other spurious sources which can also give rise to such peaks which are not due to the Majorana fermion. This is very, very important that we understand that this is happening due to the Majorana fermion or not. Because we have various applications in mind, so unless we are sure that this is Majorana fermion, we really cannot go ahead with any kind of application aspect which one has in mind as far as that's a quantum information and quantum computation is concerned. Also from physics point of view, I think it is very interesting that particle physicists did not see Majorana fermion, but if we can see on a tabletop experiment Majorana fermion, it will be an exciting phenomenon. It's not like the particle physics Majorana fermion. Essentially, it's also a particle which is its own antiparticle, and in this spirit is definitely like a Majorana fermion from the particle physics. Okay, so now so in case you are interested in numbers, so these are the kind of numbers which we have in the experiment. So the spin orbit energy scale is roughly 50 microelectron volt. The induced superconducting gap is kind of larger than it. It's like 250 microelectron volt. The Landauer factor is order of 50, and the magnetic fields which one switches on this experiment is like 0.15 Tesla, which is very tiny, I would say. I mean, when you look at quantum Hall effect, we'll talk about 7 to 10 Tesla. This is really very tiny magnetic field. The mean free path are on the order of 300 nanometers and so. So that's the material parameters. Now the physics. So what you have here, so if you really strictly want to make a one-dimensional model out of it, if it is a spin orbit coupling material, which is one dimension, what you get is 2 spin split bands. So essentially, initially they're completely degenerate, spin up and spin down bands. You have a parabolic spin up band, you have a parabolic spin down band. Sorry, can you see? Yeah, and they are on top of each other, right? That's what will happen. They have 2 bands, spin up band, spin down band on top of each other. They are completely spin degenerate. As you switch on spin orbit coupling, they kind of split, right? So that's exactly what has happened here. It's splitted, and now you see that at this point, this is the K momentum equals to 0 point where there is a level crossing. There's a perfect level crossing. Now, if you apply a magnetic field, you will generate a gap here, right? Why is it that you want to do that? Now, the point is, if you remember, what you want to realize, real materials do not give you really spinless fermions, right? We don't get spinless fermions. So one way to engineer spinless fermions is like in one dimension you have always spinful fermions, and what you are saying is, I do not want the up and down branch, I want half the degrees of freedom. At a given momentum, I want only one spin species and not both. In general, if you take any material, at a given momentum, you will get both spin species. But what you are asking for, what you are calling a spinless fermion is essentially, at a given momentum, you are desiring to have only one spin species and not the other one. So how do you organize for such a thing? right? This is exactly like organizing that. So you have a spin degeneration. So you lifted, you spin splitted them due to spin orbit coupling, then you got this degeneracy point, and now you switched on a magnetic field in an appropriate way so that you open up a gap. You see, in this energy gap, you really have this branch here and that branch here. That's pretty much like spin momentum locking. So this momentum completely decides the spin of this object. This momentum completely decides the spin of the spin degree of freedom is kind of out of the game. It is like spinless because this guy has gone out, right? So there are only two branches, you see. There were 4 branches initially, 4 degrees of freedom, k minus k up down. From it, you threw away half the degrees of freedom by opening our gap. Now what you are going to do?
Can you be a little louder?
Oh, sorry, you can't hear me? Hello?
Yes.
Hello, can you hear me now? Prabuddha?
Yes. Yes. Yes.
Okay. What I'm saying is, so what you wanted is spinless superconductivity. Now nature doesn't give us spinless superconductivity. We are going to engineer it, and the way we engineer it is that you first have to throw away half the degrees of freedom. So in one dimension, if you're thinking of any dispersion, then at each momentum you have spin up and spin down. What you want is go to a k vector and say that I'm going to throw away one of the spins. How do you do that? So that is exactly what is being designed here. You first switch on spin orbit coupling so that your bands are split. This is one dimensional band which is split, and then you see that there is a level crossing here, and once you have this level crossing, it's like, you know, zero momentum. The spin doesn't know really, because this is spin orbit coupling. So if you are at zero momentum, the spin doesn't know what to do. It is completely free. It's like spin in a zero magnetic field. So now if you switch on a magnetic field, these states are going to hybridize and open up a gap for you. That's what happened here. And inside the gap, if you could adjust the Fermi level of the material here, then you know that at the Fermi level you got spinless fermions. Effectively they are spinless, because the momentum here completely decides the spin of the level here, and the momentum here completely decides the spin of the level here. It's effectively half the degrees of freedom. Now what you do is you bring in superconductivity, and you induce superconductivity inside the gap. What you do is you close the Zeeman gap and reopen a superconducting gap. That's exactly this phenomena which is being shown here. And once you have reopened, closed the Zeeman gap and reopened the BDG gap, which is the superconducting gap, you have entered the topological regime of Majorana fermion. That's exactly a topological superconductor. So that's what these experiments were aspiring to do, and they have achieved it to a large extent. And as you can see, these are the initial data from the experiment, where I think these are not so good. You can see here there's a zero bias peak here as a function of dIdV, right? You see that? There's a bias, zero bias peak. They saw, so the trouble with this experiment was, this is in units of 2 squared over h. They of course saw a zero bias peak. They also saw reasonably good behavior as far as the kind of behavior you expect as you tilt the magnetic field, as you increase the magnetic field, decrease the magnetic field, and so on and so forth. But what they could not see is really a 2 squared over h peak. The peak was way much smaller than what they expected. So inside the gap, if you really have insulating, so there's something I forgot to tell you, that if you are thinking of Andreev reflection, if you have a piece of metal and then this metal is here, and then you have a superconductor here, you get perfect Andreev reflection if your junction here is a perfect junction. If you have any disorder in the junction which gives rise to backscattering, then it exponentially suppresses the conductance. So essentially, if you, in a real experiment, you really cannot ensure your junction is perfect. So if it is not Majorana, and if you naturally have some amount of disorder, it is expected that you will have an exponential suppression of any kind of conductance inside the peak. But here they saw a peak which was very reasonable, but of course it was nowhere close to 2 squared over h. And I think in 2019 or 18, they improved their device a lot and saw something which was very close to 2 squared over h. So this, I have not put up this experiment here, but you can look up the follow-up of these experiments here. Sorry, these experiments here, and this and these references here. You can follow up this reference. Leo Covenhaven's group has been really going after it, and I think recently their peaks have been improved to almost 2 squared over h. So that's the signature they saw experimentally. Now you can also so this is a caricature of what I'm trying to say. So I think the experiment you can think effectively is like this. You have a 1D topological superconductor, you have a eta on the boundary here, a eta bar living here, you put some ground the superconductor, you have a normal lead here, and you bias the normal lead and try to inject current from here, and what you're expecting is the conductance of this normal lead and topological superconductor is such that it gives you a conductance of 2e squared over h. That's the, in a cartoonish picture, that's the idea which they were after. I think I'm going to stop shortly. I won't go into my work. It's fine. I think you are also we are in a time when also people are trying to. I think a lot of effort has been put into realizing such Majorana modes as edge modes of 2D material. So these are not really bound state, as I said that when. So let's go back to the first slide. So we were, you remember, we were discussing that. So if you have a 1D material, here, then you expect a bound state here. But if you have a 2D material here, you expect a 1D state. So essentially, if I take two 2D topological superconductor which are distinct and make a one topological and one trivial superconductor and make a junction between them, then exactly at the juncture you expect a not a Majorana bound state but a Majorana mode to appear there, and you can start playing with dot modes. And also there's a lot of experimental progress in that direction, both theoretical and experimental progress in that direction. Another experiment which I would say is very interesting what they did is, this is I think the Princeton group, Ali Yazdani's group, where what they did is we wanted essentially spinless fermions to create that. They look strongly ferromagnetic atoms, and on a superconducting substrate they just organized this atom one by one and kind of designed a nanowire, like it's just a custom designed nanowire. You just take these atoms and put next to each other, and then they brought in an STM tip and started scanning these wires which they created artificially. And then the Indies started looking into it. They saw that there are kind of signatures of end modes where the conductance was large, and then there was a large conductance suppression as you go inside the wire. So this is also something which is quite interesting, but it's still, I think there is a lot of discussion if it is really a Majorana mode or not. But this experimental effort was, of course, very different and very remarkable. I think with that, I would like to stop and take questions.
Okay, so we thank Professor Shorin Das for a very exciting and informative lecture, and very interesting also. And you can maybe stop sharing.
Okay. I can stop. Should I stop sharing, Prabhuddha?
Yeah, just stop sharing, okay, and then we can take questions.
I stopped it. Yeah.
Right. So the session is now open for questions. Let us see if they have any questions. So participants are encouraged to ask questions. If they have any questions, they can put it either in the question and answer or in the chat box.
Participants, if you have any questions and if you want to know any information related to the topic, please put it in the chat box or in the question and answer section. So this now discussion is on for question answer session. So if any participants want to ask any question, please put it in the chat box or in the question answer section, or you may raise hand and we will be allowing you to directly ask the question.
Okay, so I have a question, which is that this P-type model. So first of all, let me say that I am a novice in this regard. I mean, I learned about Majorana fermion and P-type model for the first time from your lecture, and I have taken notes. Okay, so the question I will be asking maybe a really stupid question.
No, please ask. Please ask.
Okay. Okay. So I have worked on icing model and to some extent, and all this Heisenberg model and these things, classical Heisenberg model, etc. So normally we use periodic boundary conditions. Yes. Somehow in this P-type chain, this whole idea of two isolated Majorana fermions seems to be hinging on the fact that there is no periodic boundary.
No, but that's a very good point. That's exactly the point, I think. So the material being topological, it is basically telling you that depending on which space you put the material. So imagine a ring, a ring and an open line, right? They are topologically distinct. If you cut one, you get the other, right? So the whole argument here is that if you have a completely closed surface, closed in a sense, if you take 2D topological material and put it on a sphere, then you will not know it is topological or not from this kind of transport response, because it is just an insulator. It's only from a transport perspective. There are other ways. I mean, there are electrodynamic response like magnetoelectric effect and so on, from where you can know. But as far as transport is concerned, you will not know. It's like an insulator. But once you cut it and open it up, you will see wherever you cut it and dissect it, on those areas, you will see things growing there, which are kind of reflections of the fact that it's a topological material and it's not a normal material. So that's absolutely correct, that when you take the Kitaev chain, if you put periodic boundary condition, of course it's like a standard superconductor on a ring, and how do you know the difference? But then once you open it up, you see that there are boundary states appearing, and then you clearly know from an experimentalist perspective, you clearly know somebody else is sitting there, and from there you can get transport signatures out of it. Yeah, that's completely correct.
Okay.
But it's also, like this is something confused me a lot when I initially looking at this mapping. So when you look at this, when you take periodic boundary condition and map the Ising chain into the Kitaev chain, it's just you take the spin here and there is a non-local map to the fermion, right? And vice versa. The map is non-local. But once you open it and then try to map, that becomes very non-trivial, because the boundary is no more a boundary. It's not that because it's a non-trivial map, it's a non-local map. Your boundary will not map onto the boundary. So what is a boundary state here may not reflect as a boundary state on the other side, right? Because there the order parameter is local, everything is very local. Right? So when you try to build a dictionary, if you do not keep this thing in mind, you will really get very confused that what is happening. I'm cutting open the periodic boundary condition on the Ising side, and nothing is appearing on the boundary. But on this side, immediately a Majorana mode is appearing. And how do I make my dictionary now? But you have to be very careful in making your dictionary, because you are cutting something open. It's a question of, are you cutting something open which is local, or are you cutting something open which is non-local? I think so. The dictionary has to be made very, very carefully, and then you'll start seeing that there is a proper correspondence. Nothing, it's all fine. Yeah.
Okay. And that was my first question.
Yeah.
And the second question is that, of course, for superconductors, for topological superconductors, you can think of these Majorana fermions. But is it possible to also see it for a magnetic system?
Yes, I think you can. Yeah, definitely. People are
How do you
thinking.
see that for a magnetic
No, it's
system?
in a sense you can, if you have magnon bands, they can be topological in nature. You can have it in optics also. You have optical bands which are topological in nature. People are doing that these days. In photonics, people are doing it. So any
No,
band, in a sense,
suppose I have a wild metal or something like that.
I'll give you a worst example, Prabuddha. Think of, it's actually, as far as the topology is concerned, you don't need quantum mechanics. It's more like what you need is wave mechanics. So imagine that you really have phonons, classical phonons, and you have a phonon spectrum. You can always arrange it in such a way that the band structure which comes out due to this periodic organization of spring mass system, you can always have a band structure which is topological, which will have end modes or edge modes. Right? And I think this was something which was done in probably Pennsylvania University. They built a huge spring mass system where they saw there are sound modes which live on the boundary. You can kind of build it.
I think it's as simple as you take the standard chain, 1D chain, and cut it somewhere.
No, but will it give you this physics or not depends on what you have in the underlying lattice, right? That's very important. That is where the engineering comes in. That the usual band structure which you are used to seeing, you have to somehow invert that. And there has to be a topological distinction between the standard one and that one. If you could engineer it, you will see this even in wave mechanics. Yeah,
maybe I should talk with you more.
No, it's very interesting.
Because we are dealing more with band structure and all these things. I mean, I don't personally deal with it, but I collaborate with people who are more into material science.
Sure, and there
who
is a lot
deal
of
with,
material science here. Exactly. I think it's very beautiful that this was predicted first theoretically, and then a lot of material science, and then people experimentalists put it together. It's so beautiful, no? I mean, people came up with this BHZ model. They predicted it. I mean, they could think what material will do this. First, they understood the effective physics. Then they came up with the band structure for it, and did some band structure calculation, and then made a solid prediction, which later on people really engineered and saw. So
I see.
it's mind-boggling. I mean, if
So
you
it's
think
usually the reverse.
it's the
But in
reverse, yeah. It's not where you hit something by accident. It was not like quantum Hall effect, which was hit by accident, and then you realize it's a topological state of matter and so beautiful and so on. This was, I think, really reverse in that sense. So definitely, there's a lot of band engineering which goes into it. And people are continuously thinking of how to deform the bands and get more and more, to all kinds of distinct topological material, what you can design and so on. It's like every day's archive you see is crazy. The amount of,
So
research.
suppose somebody just wants to read about this thing. Do you have a nice review? I mean, can
Yes,
you
I think there is a
suggest
very nice review by Charles Kane and
Charles,
Charles Kane and Zahid Hassan.
Charles Kane and Zahid Hassan? In
Yeah,
which journal?
this is reviews of modern physics.
I don't know.
It's a probably it's a colloquium.
Okay, Charles Kane.
Yeah, Charles
The
Kane.
same person, Kane and Millie
Yes,
model.
yes, yes,
That,
absolutely. Yeah,
and Zahid Hassan.
yeah.
That's interesting. Okay, so I just.
And you can also
Okay,
go to Kane's webpage and see he gives beautiful talks. I mean, really fantastically clean talk. I think even KITP has a 3 set of talk by him, and also by Zhang. I think there are a series of talks by Zhang which you can look up. It's very instructive. You will really get a flavor of the subject.
okay. Because I really want to move into not exactly this thing, but in the context of material science, if we can search for topological insulators and
Sure.
uh, file metals and this kind of phases,
Yes. Yeah.
I'm sort of thinking of moving in that direction.
Sure. It's a very interesting direction, happening direction. Yeah.
Okay, so Professor Bhaur, do you have any questions? So this is our head of the department, Professor Radhavan Bhaur.
Hello.
No, no,
Hello, sir.
okay. No,
Yeah.
thank you. Thank you. I have no question. Thank you, Dr. Das, for giving such a nice lecture from the very beginning to elaborately. You have explained everything.
Thanks.
So that is also not my area. Anyhow, I have to some extent I understand, not the whole thing. Anyhow, I have got some idea. Thank you very much for giving some idea about the subject in which
No, no, absolutely.
I have no idea.
Pleasure.
I
That's
have,
something was understandable. That's
okay,
really a pleasure.
thank you for that, and thank you, Dr. Das, for coming over here, giving your time and spending some time with us for our participants, and thank you on behalf of our university to you for giving such a nice lecture in our FDP faculty development program. It is a 5 days program, and last your lecture it will end with your lecture, you can say.
Yes.
So.
Yes. Yeah.
Uh, so it is a nice opportunity for us to see you and hear you from you and our participants also. And thank you very much.
Thanks a
And
lot.
we hope
Thanks a lot for inviting me.
IJAR is very close to our university.
Yes.
So in future also we
Every time I go
will.
to Kolkata, I go by exactly close to your campus and we drive. And I keep looking at the huge building and it looks very nice actually. Yeah.
You are welcome now and see. And thank you very much for
Thanks.
giving your time and mind, everything with us.
Thanks.
Thank you, Doctor.
Thanks.
We thank once again Professor Shorin Das for a very nice talk and very, very exciting talk on a very interesting topic. And so that brings us to the end of this FDP, that's Faculty Development Program. And we thank all the participants for participating in this program. And now you can take the quiz and the feedback. and then once you successfully complete the quiz, you will be issued the certificate.
So can I leave?
Sure.
Okay. Okay.
Thanks a lot
Okay,
again.
Thanks.
thank you.
Yeah,
Thanks
thanks.
a lot.
Thank you,
See you.
Pasha.
Yeah, see you.
Thanks.
Bye bye.
Yes, sir. See you.
For all participants, we have provided the quiz link and the feedback link. So please attend the quiz and please provide the feedback so that we can bring out few more this type of programs. Is it, sir? So feedback will be help us.
Okay. Okay. One more thing, that is, I want to give my thanks to all people involved, all people. First of the Islamic University of Science and Technology, Jammu and Kashmir. We also want to thanks to them. We also thanks to the TechWeek because for funding, and also our participants because they are the mainstream, or they are the main force to us to organize such a program. It is due to their interest. If they feel good, then we'll feel encouraged. Otherwise, we have to modify it according to their requirement. So I request them to uh, convey their message to us, what way we can improve it. And again, I want to thank Prem Kumar and his team, because it is the reason by which we are able to organize it in such a smooth way. Because all 5 days they give a total effort within this short video. And I also, lastly, I want to thank my colleagues, Dr. Sannal, because he has given thanks to all without, but he has not got no thanks. So I want to give him thanks for organizing such a nice program and giving total pain with him to get it complete. And also some unseen workers are also there, my other colleagues, those who helped us in different ways. And I also give my thanks on behalf of our department, on behalf of our school, on behalf of our university, because their help encouraged us, helped us to organize it smoothly. So thank you all.
We thank Professor Radhavallo for helping us organize, for being a part of the organizing committee and being one of the driving forces for organizing this FDP, and along with our director and vice chancellor. And the participants are encouraged to take the feedback and give the feedback, and also now they have to take the quiz, and then they will be issued the certificate. Shall we wait for some time?
Yes, you have to wait around 10 minutes.
Sanil, sir. So what we are, till what time the quiz will be open, sir?
Around half an hour.
Okay, sir. Sir, 13 questions are there. So if we can give 1 hour, 1 hour
Okay,
around.
okay, no problem.
So for all participants, the quiz link is open right now and it is valid till 1 hour. So please give the quiz and please give the feedback also. And the certificates will be provided to the successful participants who attend the quiz and give the feedback. So after processing all the quiz responses, we will be sending the certificate. So it is mandatory to give the quiz.